Здравейте.
И където може картинки.
Не пуснахме това.
Отделно става, че тия са просто тук за стената.
Аха, добре. Сега като дойде, че номинал да ги слагат.
Може да ви видиш какви фишки.
Ами, често казвам, искам, обаче нямам време. Защото има още неща за настройване. Така, добре, това го пуснахме.
Вие са големи години, до всички.
Защо? Какви глупости са?
Аз съм друга връзката. Започна COVID, тази връзка трябва да е носиш, да е китайска.
Да го спрем това и да видим какъв е проблем сега.
Някъде може така това, така че да няма големи поражения. Да, може малко. Не знам как.
Аз не знам по стена.
Да, не е хубаво сигурно. Може така да това малко тук да промесваш така.
Не знам как това каже. Значи, може би с лигия.
Така че всичко ще може по-малко. Не знам,
няма да направя нещо бегано.
Няма.
Това са много страници.
Да, 20 така. Добре, да, може да поставиш отстрани. Така. Тук са голяма това. Може тук е така. Тук пиши вече. И тук е вече. Отзад малко да ги сложиш. И тук е също на тези.
На перваза.
Малко там долу.
На перваза. Дайте на перваза ще слагам.
Добре.
Защото по-добре е. Не знам да не правим вариант. Чрез Zoom сесията на институт.
После ще кажа, хайде да почне това и... Така, тук.
Те свързани ли са или не? Или са по-отделно? Така, кое едно?
Така и да ги слагате, не така, нали? аз не запретил нищо, значи оставям и да кажа сега не.
Това е хубаво на стена, ама...
Ако се да се знам, по-добре тук да се ги път така, да се викам на картачки.
Колко са?
25. Там могат да се изпълнят обект от
Значи, ако са 8 дни, много се направя да ска, те няма да се използват. Не, тази част няма как. Ще ползва от там до тук, защото камерата е на гласа, това не може. Само дясното парче няма.
Иван ми беше това парче.
Какво да правя сега?
Тук колко могат да се съберат?
Чакай, ще видим, защото той има...
Аз трябва да се сбъркам по въпросите. Къде могат да се сложат тези неща? Което не си се няма.
Едната може да се сложат малко.
Лошото е, че това след като следваш има опасност да се сложат за да ги
Тук са нети 9, така?
тук на тази дъска е на вратата. Или в пакта или пък другия вариант е така, горе ли са, горе ли тихичко?
Не, аз...
Тук може на това вероятно да се наредят. Така, без да не се да това. И ако не стигне, може да знам. Отново само, ако има ли значение начина на подредба? Добре, дай там вертикалните да слушам. Видите?
Да.
Сега да знаете, по 32 вертикални. Още един и на долу те може да описат малко. Историята трябва да са така.
Само че не си го дава оригинала. Не си го дава оригинала.
Трябва да затъмним. Ани, трябва да затъмним отпред, иначе на екрана не е добре. Да пуснем тия. Според мен трябва да пуснем. Ами да, три вертикално. Много да ни казвам.
Аз ще спомням нещо, което имаше на вашия група на документацията, там да се това ще бъде това. Само, че някак и да го мисля, как да запада.
Добре, че взе стария вариант.
Удобно се припомня. Удобно се припомня различни случаи.
Може би като се затъмниш.
Не повече от това не може да се затъмня. Това да може да се върти. Трябва да се следва да видим на това на
Да. Айде, няма ли някакво всякакъв да знае.
един катастрофиран. Сега по шофьора, Джони. Той и затворява и както се чете плата, без плата, той ще Сега се оказа, че имам безпоение на сега вече от една седмица първи като било имам 3 месеца, който се чекни. Аз сега нямам тия пак се не знам. Как се
Кой си разприказва сега?
Може би МСГ. Може би това е съседната страна МСГ. И се разгледа като бяха съвсем случайно следващия непримърна и едно такова. Така че...
Да остава някой така. И другите ще ги лепна там. Там ще да лепам, а там те, понеже са на широко, по-малко ще се съберат. А вие искате ли ги някъде да ги четете? Всеки да си чете.
Да. Или аз ще те взема. До края на средната получена на скат. Да.
Да, много гадно. Ще се съжаля, че я няма да се
And you see, here's some information about the early career of Vesselin. He graduated from the University of Sofia, then he went to do his military service, and I recall, in fact, I was a school student at that time. He taught us some courses for training classes, and of course dressed in his army uniform. Then Vesselin got his PhD from Moscow State University in 1979, and a year later he was appointed at the Institute of Mathematics and Informatics. He worked there until beginning of this year, when he retired. Okay, likely his retirement was rather formal, and I am sure were not the COVID restrictions, he would have stayed in his office at the institute more often than most of our younger fellows. But it is my personal opinion, of course. Then some more information about Vesselin's career. You see here he became associate professor in 1986. Then he got his habilitation. It is called Doctor of Sciences in Bulgaria, 1998. Professorship in 1999. Corresponding member of the Bulgarian Academy of Sciences and member of the Bulgarian Academy of Sciences in 2004-2012. He was the chair of the algebra section at the Institute for more than 10 years, chairman of the Scientific Council of the Institute. Then for 4 years, he was the director of the Institute of Mathematics and Informatics, and was and still is involved in very many governing bodies. But in spite of time and energy consuming administrative duties, Vesselin has always been actively involved in research, very actively, I would say. And the main area of Vesselin research is combinatorial ring theory. That's why the name of the conference. And his research interests include, but are not limited to, PI-algebras, numerical invariants of PI-algebras, symmetric functions, commutative, non-commutative invariant theory, polynomial and free algebras, relatively free algebras, automorphisms and derivations, group representations and applications, computational approach to PI-algebras, and many others. And his main contributions to algebra and related mathematical topics, okay, of course I cannot list everything due to lack of time, space, but let me mention some of them more or less in chronological order. First, the construction of finite dimensional Lie algebra over a field of positive characteristic P without finite basis of identities. Then minimal basis of the identities for the three-dimensional simple Lie algebra and for the full matrix algebra further over a field of characteristic 0. Then a development of methods based on the representation of the symmetric and general linear group in the study of PI-algebras. Okay, this is a rather generic but very fruitful approach to polynomial identities. Then explicit computation of the Hilbert series of the variety generated by the full matrix algebra of order 2. A description of the identities and the central polynomials of low degree for 3×3 matrices. Then construction of central polynomials of low degree for matrix algebras. And in fact, the lowest known degrees. various deep results concerning automorphisms of relatively free algebras, an analog of Hilbert-Nagata theorem in non-commutative invariant theory, various detailed descriptions of numerical characteristics of algebras of invariants, a proof of the Anyck conjecture in its long form, an elementary proof of the conjecture of Nowitzki, and very many others. I'm not going to discuss all of Vesselin's results. Of course, Vesselin's contributions to algebra cannot be limited to the ones I listed. So he is the author of two very nice books on polynomial identities, and these are considered nowadays fundamental for and by many graduate students who are going to do research in PI area. And Vesselin was among the editors of several large conference proceedings. He is the editor of Serdica Mathematical Journal. Then a bit about student supervision. I know of at least 4 PhD students who are supervised by Vesselin, and at least 10 more where he was either official or unofficial second supervisor. Probably some 15 master students, and you see most of them did their master with published results, and in most cases it was enough for a PhD thesis. And Vesselin also supervised at least 10 postdoctoral fellows. And some recollections of the time when I was a PhD student under Vesselin. So some lessons I'm trying to put in action with my students. I'm not going to read all this, but only show this list. And now Vesselin visited very many foreign universities and research institutes. He gave courses, talks, and so on. I'm not going to list them all. First, I'm not able to. Second, the list would be immense. But let me show several pictures, probably ones that were not shown beforehand. Okay, this one. You see the date. And finally, we wish Vesselin very many more years of energy and good health, and clearly very many new and deep theorems. And happy birthday, Vesselin. Thank you.
Thank you, Plamen. This presentation is on behalf
So
of
I'm going to stop sharing this screen.
Okay, this talk, as Plamen said, is on behalf of the organizers of the conference.
Let's thank Plamen once again. And now it's time to start with the lectures adhering to the program after some short break.
5 minutes break to refocus entire group.
In 5 minutes, we'll start already with the lectures, adhering to the program. The conference will take place on the 4th floor in room 403, as well as via Zoom. You can find the link to the virtual conference hall on the website of the conference. Thank you all for attending the opening ceremony. Plamen will chair the first session.
So I would suggest that in 1 minute we start. Shall we start then? It is the first session of this conference, and it is my pleasure to announce the first speaker of today. This is Professor Yuri Bahturi from Memorial University of Finland.
We decided to have a 5-minute break, so in 5 minutes we'll start with the first one. It's okay?
I do not mind.
Okay then.
Okay, thank you.
Okay, seems some technical reasons for short break.
Recording in progress.
So let us start then.
I'm here.
And it is my pleasure to announce the first speaker for this conference. This is Professor Yuri Bakhturin from the Memorial University of Newfoundland. He is going to speak about delta sets and polynomial identities in pointed Hopf algebras. Professor Bakhturin, you have the floor.
Thank you very much. Can you hear me well?
At least for me, fine.
Fine. Okay. So, of course, when I was preparing this talk, I embedded some photographs into this because it's a talk for the Vesselin conference, and some of them I already showed. So please do not be surprised if you see the same pictures again. Also, that's not to be a very long talk, as I understand. So I will show you some pictures and some main results, not to make it an extended talk. So first of all, this talk starts with my first photo of Vesselin, which I showed already. That was in Moscow when Vesselin was coming to us, to Moscow State University as a researcher. And by the way, at that time, a paper was written in which a result is shown, which was forgotten for quite a while. That was the upper bound for the codimension growth in any algebra. So that was done exactly that time. Now about this contents of this talk. In a joint paper, which already published in Algebra and Representation Theory with Sarah Witherspoon, we survey a vast array of known results and techniques in the area of polynomial identities in pointed Hopf algebras. Some new results are proven in the setting of Hopf algebras, appearing in the papers of David Redford and Nicholas Andrushevich, Hans-Josef Schneider. We also discussed the so-called delta set in pointed Hopf algebras. They play a crucial role in PI theory, but prove to be useful in other situations. So, just quick reminder of trivial things. Every finite dimensional algebra is a PI algebra, polynomial identity algebra, with dimension of algebra is n-1, then the algebra satisfies so-called standard identity. At the other extreme, commutative algebras of any dimension satisfy the commutator identity. Generally, for any PI algebra, there exist numbers m and n, such that a power of standard identity is an identity in R. An important theorem of Amitai-Regel says that if A and B are PI algebras over an arbitrary field, then A tangent B is a PI algebra. A corollary of techniques of Regel's theorem, which is useful when dealing with quantum commutator structure of an algebra, is the following. So we define a quantum commutator for a real number k as AB minus QBA, maybe in complex numbers, just the number of the proposition. Suppose that an associative algebra over a field satisfies a non-trivial polynomial identity of degree d. Then n equal to 3d to the power of 4, if n is such number, then for any q in f, A satisfies a polynomial identity of the form which is written here, number 2. So what is in this formula are Q commutators. So usually people have usual commutators here, but this same formula is more or less the same arguments is true for Q commutators. And that is useful for looking into certain Hopf algebras. pointed algebra. So if H is a PI algebra, A is a Hopf algebra, then the following claim is true. Suppose that a Hopf algebra over a field F satisfies a non-trivial polynomial identity of degree D. If n is 3d to the fourth power, then H satisfies a non-trivial identity of the form. So if you look here, it's more or less the same thing, but instead of commutator, we had a joint operator. Add x1, add xn, applied to permuted variables y sigma 1, y sigma n. So in a moment, I will give a more precise definition what is operator add x1, a joint action of the Hopf algebra on itself. The proof of this theorem, which was proven in a paper of Kochitov, and here attribute this to myself, it's given for smash products of this form. However, the proof works in a more general situation without any changes. So that's already placed in our paper with the estimate n equal to 3d to the fourth is borrowed from a 2002 paper by myself and Viktor Petrovsky on polynomial identities in smash products. An important fact used is one of motivations to study PI algebra is the common theorem by Erwin Kaplansky that R be a primitive algebra satisfying a polynomial identity of degree D. Then R is a central simple algebra, and the dimension of R over its center is at most D over 2 squared. It follows from this theorem that an algebra satisfying a polynomial identity of degree D cannot have simple modules of dimension less than D over 2. Under some mild conditions on the field, if R is semi-primitive, say F is equal to N, F is C, then the converse is also true. Okay? So, the above theorem is useful if one wants to prove that an algebra is not PI, thus produce an infinite dimensional simple module for R. I quickly remind that the Hopf algebra is an unitary algebra endowed with co-associative coproduct, delta, co-unit, and antipole. Delta and epsilon are homomorphic mode algebras, S is an antihomomorphic. In the case where H is a group ring, the group algebra, delta of G is given by this formula, co-unit and antipoles by those formulas for all G in G. In case of invariant algebras, this coproduct on co-unit and antipole on primitive elements on the elements of the Lie algebra are defined by this formula. A convenient tool is Sweetless notation. Delta of H is written like the sum of tensors, and which is the short form of delta of H written this way. Now this add H, adjoint operator, is defined by this formula. We take H1, A, and antipode of H2. So in the case of groups, this becomes the usual conjugation, and for group-like elements, and add X of A is equal to XA minus GA inverse X plus two primitive elements. That is elements for which the coproduct, is given by this formula. H2 co-commutative if and only if the tensor H1 and H2 is symmetric. H is pointed if all simple subcoalgebras are one-dimensional, connected if F times 1 is the only simple subcoalgebra. So a well-known theorem says that if you have a pointed co-commutative algebra over a field, suppose that G is a group of group likes of H and H naught is a connected component. Then G acts on H naught by conjugation, and H is isomorphic to the smash product H0 smash FG, where the isomorphism is given by this smash. An algebra over a field is PI if and only if its extension to algebraic closure of F is PI. Since the condition of pointedness is automatically satisfied if F is algebraically closed, this theorem essentially reduces co-commutative algebras to the smash products of connected co-commutative algebras and group algebras, where the group acts by algebra automatically. A number of important results given necessary and sufficient conditions under which certain important smash products satisfy non-trivial polynomial identity have been given by several authors. Well, there is a long history. I can talk some names: Passman, Latushev, Petrogradsky, Kochetev, myself. Many of these results can be found in the Webreuter monograph, Infinite Dimensional Lee Superalgebras, by myself, Mikhailov, Petrogradsky, Zaitsev. I will abbreviate it as DMPZ. And one of the latest results in this area appears in this paper. It belongs to myself and Sarah Witherspoon. It's kind of expected, but nevertheless, it is new and it is published in this paper. So I will not give you all the details because I don't have many time. And it's just similar to those results which were obtained much further. If L is a color-Lie superalgebra or a color-Lie P superalgebra, then it is not known if these conditions are guaranteed that A is a PI algebra, if they are necessary or not. Now, delta set. The definition of a delta set in general for algebra was given by Bergen Passman as follows. So generally, delta set is something like generalization of a set of sets of elements with finitely many conjugates or finite four-dimensional centralizers and things like this. So in general, Bergen and Passman define a delta set in algebra in the following way. If you have an antipode in a Cope algebra, then there is a right adjoint module action, inner action, as I defined before, and it is given by this formula. We can define delta set H sub fin by setting H sub fin is the set of all x such that dimension of the all adjoint actions applied to x is less than infinity. Okay, so it's kind of the elements which have big centralizers. H fin is an F subalgebra, but not necessarily a Hopf subalgebra. If we set CH of x by this formula, then we can say that H fin is a set of all H such that for dimension of centralizer is less than P. If T is a subset of H, which generates H as an algebra, then X belongs to H fin if and only if X is contained in at C stable finite dimensional subspace of H. So the importance for polynomial identities is that if we want to prove that some algebra is PI, then we want to show that the H fin is of finite dimension, or even better, if the whole algebra is coincides with H fin. So the delta sets are fairly closely related to the delta sets defined earlier for the groups and Lie algebras. For the groups, this is done by Passman. For the algebra, it first appeared in my paper in the Journal of Australian Math Society in 1974. Now propositioned by Bergen and Passman, the following are true. If H is a group algebra, then H fin is just F of delta set in the group G. If L is a restricted Lie algebra over a field with characteristic Q greater than 0, and H is restricted enveloping algebra, then H fin is just restricted enveloping algebra over delta set of Lie algebra. And if L is a Lie algebra over a field of characteristic 0, H U of L is enveloping algebra, then delta L is the join of all finite dimensional ideals of L. Then H fin is U of delta L. So it's more complicated in characteristic 0 than in characteristic P. So there are some properties of delta sets. I will not mention them. They are not subspaces, but you can take the closure, the subspace generated by them, and handle somehow. So there are some properties which allow to deal with delta sets. Now, a few words about pointed group algebras. One of the simplest examples of pointed group algebra was given by David Redpath. An algebra F sub Q, Q is in Q, is generated by one group like element G and one primitive element X, such that the delta of A is group like, that is Q primitive, and they commute up to this scalar Q. So the Q commutator is equal to 0.
So, simple theorem, an algebra F sub Q satisfies a non-trivial polynomial identity if and only if Q is a root of 1. If Q to the n is 1, then H equal to F sub Q satisfies the standard identity, which is written here. And 2n is the minimum degree of all identities in F2. So this is a simple algebra. Everything is clear. Everything is known. In BMTZ book, the author have constructed an irreducible module for a color polynomial algebra in two variables. Following our notation, one should consider a vector space V with this basis Vi to make it an F2 module by setting A epsilon Vi shifted left to the left and x to the right multiplied by e to the power of I. Proposition: if Q is not a root of 1, then V is an irreducible F sub Q module. Proposition: if Q primitive nth root of 1, then V sub n is an irreducible F2 module. So, don't know whether we define V sub n, but this is just a cut of this module V. If Q is an nth primitive root of 1, then FQ satisfies an identity of degree to n, but no identity of degree less than to n. Delta sets in FQ. Let Q be an arbitrary field. Q is a non-zero number. Define H as before. Maybe Q was non-zero number always. Note that delta of X is equal to this. Antipode is equal to that. Recall the definition of delta set. So delta set is all H such that the dimension of capital H applied to small h is less or equal than I. And H pin is just the definition of the above set. Theorem: H pin equals to H if and only if Q is a root of unity. Moreover, if Q is a primitive nth root of unity, then delta n of H is equal to H, not just the union, but for a very particular number n. So this results about FQ are generalized to much more general pointed algebras on Drensky and Schneider. They were introduced in their work on the classification of finite dimensional pointed algebras. So it's not very far from the classification of finite dimensional pointed algebras, but this is important for particular case. So let gamma be an abelian group and gamma hat to the dual group with identity element denoted by epsilon. Let theta be a positive integer. It's one of the features of Drensky's paper where the natural number is denoted by Greek letters. And this matrix is a cardinal matrix of finite type. For each I, we consider some element Gi in the group and characters in the group such that chi I of Gi is not 1, and this condition is satisfied. Chi I of chi j of Gi and chi I of Gj. Okay, so we denote this number Qij as a value of character, j character and the ith element, and call this collection, group, set of elements, set of characters, and the set of matrices, the pattern of finite abstract type. So we have a vector space. Suppose we have a vector space with basis x1 as theta. Define the action of gamma on V by this formula, natural formula, and coaction by this formula. Delta xi is vi tangent xj. So J kind of graded by degree vi. Then V is a Jeter-Drensky model over K gamma. The tensor algebra Q of V is a braided algebra in the Jeter-Drensky category. It's no time to explain all of this, where the braided coproduct takes xi into xi tensor 1 plus 1 tensor xi for all I. Define braided commutators. So these are those commutators which will appear in the identical relation. I choose scalars lambda ij with some restriction on indexes, for which lambda ij is equal to 0 if gi times j is 1, or chi j is not identical. Let H be algebra defined by underscore Schneider to be the quotient of the Smash product. And by this relation, cell relations and linking relations. So cell relations are more or less the same as in the definition of simple algebra. And there are some more relations, linking, connecting different components. As a algebra, we have this structure. So the elements of G are group-like, Xi are primitive. So these are the values of co-unit or antipode for all elements. Thus, we see that F sub C, as defined above, becomes the adjoint action of the algebra U of D of lambda and itself. Note that H has a PW basis, on a reduced basis, determined by the root vectors corresponding to primitive basis. So here I give some examples of positive algebras. For instance, these quantum groups, so-called, or positive types of quantum groups. I'll just skip this. So also FQ can be generalized to more generators rather than one group-like and one primitive. There could be many more of those. They can correspond to the Cartan matrices of the type A1 cross A1. So, and now I want to just to more or less finish by giving you the result, final result of this paper. A slightly more general version of algebra U of D of lambda appears in the datum. The group was gamma abelian, but we don't need to assume this for our theorem. Instead, we need to request that gamma 1, gamma G1, G theta, the element of the group, belongs to the center of the group. We deal with this more general algebras in the next theorem. So the theorem is this. An algebra H of type U of D of lambda, D of atom, lambda is a collection of numbers, satisfy the polynomial identity if and only if gamma has an abelian normal subgroup gamma bar of finite index, which contains the center of gamma, and hence it contains the elements G1, G2, the multi-center. The orders of all characters, phi 1 up to phi theta, are finite. So these are necessary and sufficient conditions for this algebra to simplify a polynomial identity. And one more result, and that will be exactly on time, to the end of my lecture, is the following. Suppose that H is a U of D of lambda, then H pin is equal to H, so the delta set is the whole algebra, if and only if gamma is an FC group. FC group means that every element has finitely many characters. And the orders of all characters, phi 1, phi theta, are finite. Okay, so these are some of the results of the paper I was talking about. I had to cancel more than a half slides from the paper, which I prepared originally, but I felt that there was a shortage of time. So now I think I'm on time to finish, and then just quickly go through the process, which I showed already. Thank you very much. That's all. I finished.
Thank you, Professor Bakhturin.
So if there are questions, I'm ready to answer.
Let us thank Professor Bakhturin. And now I would like to ask whether there are some questions, comments, remarks about the talk. Any comments?
Plamen, maybe I would like to ask one question to Yuri.
You are
Is there
welcome.
any, thank you. Is there any relation with the finite dual of the Hopf algebra? Because it sounds like some generalization. It's simply a remark.
No, I don't think that there is a connection with finite dual.
Thank you.
Any other questions?
Yeah, I have a question.
Welcome.
I mean, you talk about the analog of Passman and Isaac theorem for group algebras, and this is really very nice. The question is about the Hopf-commodule algebras. Hopf-commodule algebras that the commodule structure is strong enough, and this will give you the conditions that you have in the theorems. So if you can grade, or if you can put a commodule structure that is not a, it's a real commodule structure, and not a fake one. Otherwise, you cannot say nothing. You can say nothing about the Hopf algebra, but if it is not a fake one, then you can say things about the Hopf algebra.
Can I answer?
Yeah,
Of course.
yeah, of course. Thank you.
Well, you see, a lot of stuff hidden here is about smash products and red hat products. So if you use your commodule algebra to include it or to represent it or include it into some smash product, that would be a sensible question to ask what are the conditions under which they satisfy the element. I think it's a reasonable thing to think about.
So, are there any other questions? Then let us thank Professor Bakhturin once again. And we'll have some 6 minutes break till the next talk.
non hanno detto niente, dovrei parlare fra 2 minuti. Non mi stanno comunicando. Non stanno...
Un po' comunicare.
No, a meno che non abbiamo cambiato il programma, in caso di saluto e arrivederci.
Un po' in te.
Ah, io devo scrivere screen. Aspetta, mi ha mandato un messaggio, screen. Like. Mm-hmm. 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 You hear me?
Yeah, very clear.
Okay. And you see the screen?
Yeah, but
sorry.
it is some picture.
Okay, because I will put it in full mode, in full screen mode. Okay, do you see everything?
Yeah, the picture.
Which picture?
Okay, it is some sort of a drop of water drop.
You don't see the file?
No.
You are screen sharing. I don't know. I don't know what's happening because I'm sharing the screen.
Have you opened the PDF file or whatever?
Huh? What do you see?
Very nice drop water drop.
And there is no water.
Some green, some shades of green.
I have no idea what's because on my screen I have the file, so I don't really know what's happening. Let's go back.
Probably you choose share screen and then choose the correct file. It will show you some dialogue.
That's what I did, but let's see. Zoom. There is some problem. New share. Let's try new share. What do you see now?
The same file, the same image.
Just a second. What about now?
Now it is excellent.
Huh?
Good.
Now it is okay. It is the Weingarten function.
Okay. Okay. And now I hope, is this still the Weingarten function?
Yeah.
Okay. So somehow there was some problem. I don't know. Anyway, I'm ready whenever you want. So should I start or not?
Yeah. Let us start the next talk. It is with immense satisfaction that I announce Professor Claudio Procesi from the University of Roma. And he is going to talk about the Weingarten function. Professor Procesi, please.
Thank you. So I'm so happy to participate, even if from very far away, to Vesselin's 70th birthday. And I hope this talk will be of some interest to you. It's, you will see, basically a lot of things about the symmetric group, something very classical, but in a very different shape. Okay, so the topic actually covers several different areas: invariant theory, Fourier analysis, non-commutative algebra, and so on. And let's start from the very beginning. What is this function? So the name actually is due to Collins, but this concept appears already in some work of Formanek on central polynomials, of which you must know. So one starts from the group algebra of the symmetric group, but we take with coefficients in the rational functions in one variable d, which eventually will be specialized to some dimension. So that's why the name d. So we start with a very simple element, which we call PDN, which you can see here.
Claudio, you are not showing, you are showing still the first page of the presentation.
Pardon?
You are, we don't see
the... oh, to the front. Oh, shoot, what shit. What's going on? I don't understand. I really don't understand what's happening.
No, we see the beginning of the presentation, and now you should scroll down.
Yeah, but I'm moving.
Ah, you are moving.
It says sharing is paused. I don't understand why it says sharing is paused.
I think I know what the problem is. You open you click on the PDF file, and then you navigate from the PDF file, not from the screen in Zoom.
Yes, but what am I supposed to do? Pause recording, pause recording. Maybe
recording stopped.
Resume share.
Recording in progress.
Let me try to understand what's going on. Resume share. I don't know, I never had these problems with Zoom. Resume share. Oh shit. There's a new share. I don't know what's going on. This is a mess.
Had you could stop sharing everything and start again?
I'm trying to make sense of this thing, but I don't understand what's going on. This never happened to me.
Then probably you stop this sharing of the screen and start it once again.
Oh, now it's...
no. Now it is okay.
Let's see if it's okay, truly okay.
It is integration on the unitary group now.
Yes, but I wanted the previous page. So how do I get the previous page now? This is a complete mess.
Probably go to the PDF file, not to the Zoom screen, but you choose the PDF file, and from it you navigate page up and page down.
This is going to be a complete mess. That's what I'm doing. I'm using the PDF file. Okay, let's see if that works. What do you see now?
Some Fourier
integration
analysis.
on the unitary group. This is not as simple as Fourier analysis
No,
on the torus.
You still don't see what I see. I mean, there is no connection between what I see and what you see. I really don't understand what's going on. Sì, ma ritorna indietro. This is not going correctly. I really do not understand what's happening.
Then a solution might be to stop sharing and then the Weingarten function and invariant theory, Fourier analysis, non-commutative algebra. Is this
This is what I see now.
way?
Now, suppose I push this. No, it doesn't. The file does not proceed.
Claudio, sorry. Perhaps you have open Zoom in two places. Also, perhaps you have open also Zoom in the navigator, in the Explorer, in your Internet Explorer, because if you have two windows for Zoom, you have this kind of problem. Your browser? Are you using a browser? An internet browser?
I don't know. I've just used. I think I'm because okay. Let's see. What do you see now? Pardon?
The Weingarten function is the title, and then you have invariant theory, Fourier analysis, non-commutative algebra.
So it's not. Let me do one thing. Let me connect again with Zoom. Let me leave Zoom, and I will come back to the Zoom meeting and. Can you see? Can you hear me now?
Yes.
Yeah.
Okay, I'll do again. I'll try again to share screen and see what happens. What do you see now?
The name is due to Collins, but it appears already in work of Formanek.
Okay, this is what I see, but let's see if it proceeds. Oh, now it has changed?
Proceeds.
Huh?
Yes.
Yeah.
Okay, so maybe now it's working. Let's see. If you still have problems, so let me know. Okay. Now,
for sure.
So we start from what I said. You start from the group algebra of the symmetric group with coefficients in the rational functions in D, which is will be a dimension. And we start with the following element: the summation on the symmetric group of D raised to the number of cycles of sigma, and then times sigma. And I have the example on the bottom of the page for the symmetric group on three elements. We have three conjugacy classes, and you have D cubed, then D squared plus the conjugacy times the conjugacy class of transpositions, and then D times the some more conjugacy class of cycles. Now I push this thing, and I hope we get the next the next page. Do I get the next page?
You exist. You exist.
Yes.
Yes.
Okay. So now the fact is that this element is invertible and central, and so by definition the Weingarten function is its inverse. And here at the bottom of the page, I have written down the explicit formula for the Weingarten function for the symmetric group on 3 elements. So I write A, the sum of the first conjugacy class, and B, the other conjugacy class. And here you have this rational function with the denominator, which is very special, as you can see, and this would be actually true in general. Actually, it's a very complicated thing to compute. And, but I have to explain also why you do this, because a priori it does not seem to be such an interesting object. So the point is that when D is a positive integer, I hope you see this, then we have that D to the number of cycles is the character of the representation of the symmetric group on the tensor power of V of order n, and V has dimension D. I'm sorry, V has dimension D. So if you take this permutation character is D to the C sigma. And as soon as the D is greater or equal than, so the dimension is greater or equal than n, then this function evaluated at this number D now is still invertible. And you can see because the denominator is non-zero. And then you define again the Weingarten function as its inverse. Now it's a function with rational coefficients. Okay. Now, why is it important? So this Collins uses it for integration on the unitary group. So what you want to do? You want to integrate over the unitary group some polynomial in the entries of the matrix. So unitary group is a set of unitary matrices, and the Uij are the entries of the matrix. You take a polynomial in the entries and their conjugates, and you would like to know what is the integral of this polynomial. And it turns out that unless in this expression here K1 is, if K1 is different from K2, then this integral is 0. And when K1 is equal to K2, this integral has a formula, there's an explicit formula, which is actually based on the Weingarten function, which I will give you in the next transparency, I hope. So this is the formula. Here it is. The integral of this thing, you have to write somewhat compactly, otherwise it becomes unreadable. It's the sum of the pairs of permutation of the symmetric group on K elements of this number, which are 0, 1, and then this Weingarten function associated to the product gamma sigma minus 1. So this is a rather remarkable formula because it's something you can compute, and it gives you sort of basic terms of Fourier analysis on the unitary group. Now, why this formula? Let me give you a sketch of the proof. But it's essentially the proof. So the idea is the notion of representative function on a group G. So if you have a finite dimensional representation of group G, then a representative function on G is something of this form. It's obtained by taking the matrix of G, applying it to a vector, and evaluating it against some linear form. So this, if your phi and b are fixed and G is variable, this is a function on G, and this is called the representative function. So basically, a representative function of UD acting on matrices by conjugation is actually this thing here, which is here, the multiplication of entry UJH times an entry U bar IP. Okay, so these are basic representative functions. And then if you take the tensor power of these matrices, then you have that since the product of representative functions is a representative for the tensor product. You have that this basic functions which we wanted to integrate, these ones. Okay, no, this one. This is just a symbol, and this is the product of this thing. Is representative function for this particular representation. And so the idea is that how do you integrate representative functions? And this is an algebraic problem. It's not an analytic problem. And what you have to do? Okay, so here perhaps is not so important. It is the explanation why this thing, in fact, is a representative function. It's how it is represented. Anyway, this is a representative function. And now, when you integrate is the same, this formula, you have to do this formula. But then in this formula, what you have the map of integration of a vector multiplied by the group. So this is just the average of the transformation of the vector under the group. So this is the projection of the vector space to its invariant vectors. So this is very general fact. You have a linear representation of a compact group, and you have the invariants, and then if you want to project to the invariants, you just have to integrate. So this means that knowing this integral is the same thing as knowing the projection. So now the projection in a given representation, perhaps you can find a formula which is algebraic. And so the problem is, what is the algebraic formula for the projection in which case? In the case of this map of the representation, one representation is the endomorphism of V tensor K, and then the invariant of this representation is just the image of the symmetric group acting on the V tensor K. This is a sure-while duality. This is one of the basic facts of tensor algebra. So you would like to find the projection from this tensor power to the algebra generated by a symmetric group. And now you start from this map, which is very easy to define. You take an element of this tensor power, and you just take the trace of this element against the inverse of permutation, sum over permutation, and you have a map, an equivariant map. The point is that this map is not a projection, but we will construct a projection from this map. So again, the question is, how do we write the equivariant projection from this tensor power to the algebra generated by a symmetric group? And the fact is that if you restrict this map phi to the space to which it should project, then you see that this is just a multiplication by this element, which then you need to invert. So the projection is obtained by composing this map, which is equivariant, but is not a projection. And you compose it with the inverse of this map restricted here, which is the Weingarten function. So here is the formula of the equivariant projection. It's the Weingarten function times this more elementary formula. Let me give it again, the formula. The formula is, oops, sorry, this went out. This is going to be a mess. Okay, this is the simple formula of this map phi, and then from this map phi, you compose this map phi by the Weingarten function, and you have the equivariant projection. And from what I said before, from this, the formula of integration of Collins follows quite easily. So let me now say a few words about how do you make this computation of this Weingarten function. This again is basically sure-by duality. So from classical work for Benius, sure while, if you want, you know that the tensor power of a vector space decomposes into the direct sum of irreducible representation of a symmetric group tensor, the irreducible representation of the linear group. And the representation of the symmetric group are indexed by partitions, and the partitions which appear are the ones of height less or equal than the dimension of V of the vector space V. So this thing S lambda V is the Schur functor, which is irreducible also as a representation of the unitary group by the unitary trick, if you want. And now this is a standard definition when you do representation theory of the symmetric group. You take a partition which is described by a Young diagram. You take an element of the Young diagram, then you define the hook number and the content. These are these two numbers, which maybe the formula is not so transparent, but I will give you an example. Okay, so if you have this
There seems to be some problem. If you are hearing me.
I hear you.
So we'll have to wait a bit. The internet connection seems sometimes is behaving in a strange way. Okay, we'll wait.
Plameny will be right back.
I'm here.
I see.
You see?
Yeah.
Okay, let me just tell you. This is a nightmare today.
I close.
Okay. About cookies. Okay, because yours, I'm screen sharing. Oh. No. Aspetta, sì, no, dove cavolo stava la pagina? About reader. open PDF of the last session. Okay, do you see it again?
Yes.
I'm sorry, this is somewhat, this lecture is not started on the best. Okay, let's see. Where we were, sure by duality. Okay, I hope. Okay, are we back to where we started? Hello?
Yes.
Yeah.
One more.
Okay, so I have the hook number and the content number, and then I hope it doesn't die now.
We were here in the example, yes.
So here you see two diagrams, two young diagrams, one filled with the hook numbers and the other one filled with the content numbers. I hope you see that. Okay?
Yeah.
Yes.
Correct.
And with these numbers, one has the two formulas, which give the dimension of the two corresponding representations of the symmetric group is the hook formula, the standard hook formula, this one, k lambda 1 and k factorial divide the product of the hook numbers. The other one is a very remarkable formula by Stanley, which is the dimension of the corresponding representation of the linear group, which now depends on D. But the remarkable fact that it depends on D in its very simple form. The product over the entries of the diagram, and you have D plus the content divided the hook. So this is a very, very beautiful formula by Stanley. This is called the hook content formula. Now, with these two formulas together, you have that the Weingarten function is given by this formula. Now, you can look at it, read it. It's in any case, it's a rather complicated formula. But here, the fact is that the parameter D appears only here, the denominator via this S lambda of D. So this is a rational function of D with poles of these things, okay. So this is very explicit, but it's not very easy to use. In fact, it's not even clear from this formula when is this zero, when it takes negative values, positive values, and so on. So the only case in which this formula can be explicit is when sigma is a full cycle, and this first computation is due to Formanek, which gives this formula here, which he used for central polynomials, as I hope we will see later, if if we don't have any other disasters. On the other hand, Collins has a general formula, not just for D equal K, but for all D, and which is this formula, which involves the Catalan number. So the Catalan number is this number which appears in combinatorics in several different ways. I think there is an entire book of Stanley in which there are 100 ways in which this Catalan number appears. And it appears also here. And here is an example. You can do whatever you want to say. These are C11, C2, and so on. These are the sum of the conjugacy class relative to this partition. So you have the partition 1, 1, 2, and the conjugacy class is the sum of the. Okay. So this is there are a few examples. So I computed up to D equal 14. And then there is this remarkable conjecture that the absolute values are strictly increasing in the lexicographic order of partitions, but written in increasing order. Now, the fact is that by chance, doing the computer, I had this funny order, which would not be so natural. And then in this funny order, it appeared this phenomenon. So if you see it again, you see if these numbers decrease 1015, 299, 160, 115, 101, 74, and so on. So it's just a chance which this thing appears, but I have no idea how to prove this conjecture. So let me give an idea why this applies to random matrices. One of the ideas of statistical mechanics is to study Hamiltonians of large sets of particles as random matrices. So you want to study the asymptotic behavior of integrals of functions of matrices. So you take a function of matrix, you make the matrices go to infinity, and then you want to see how the asymptotic behavior is, because this gives you statistical mechanic formula. So this with mathematical physicist Don Weingarten pioneered this computation for integrals on UD, on the unitary group, as d goes to infinity. And then it's interesting to study the asymptotic behavior of the Weingarten function as d goes to infinity. And here there is this theorem. So you have, first of all, you have to introduce a standard notion in the symmetric group for this absolute value, which is the minimum number of transpositions whose product is sigma. So, of course, for example, transposition, the absolute value of transposition is 1, the absolute value of a 3-cycle is 2, and so on. And then it turns out that there is a connection between the number of cycles and this absolute value, because this absolute value sigma in the symmetric group with k elements is k minus the number of cycles of sigma. And now again, with using the Catalan numbers, we can define this number for a partition, or for a sequence, a partition, and for the partition just made of one entry of it is just the Catalan number k minus 1 with a sign. For a sequence of numbers is the product of these numbers. And then there's this remarkable theorem of Collins, is that you have this limit, which is gives you asymptotic behavior of the Weingarten function for a given permutation sigma. You multiply by d to the k plus this absolute value, and times this thing, and this gives you this product of Catalan numbers with some signs. Actually, the paper of Collins, I think the proof is completely wrong, but it makes no sense. But in any case, it was then proved by Novak, and then I found a very simple proof using the following ideas. So the first idea is somewhat clear but complicated. You try to write the inverse in power series. So you write this element as d to the k times 1 plus the remaining thing, and the remaining thing by the previous formula are the sum over partitions of the sum over the conjugacy class and d to the minus of this absolute value. And so then you invert by geometric series. You just take the inverse as a geometric series. But then, of course, when you invert as geometric series, it's a mess, because you would have to know the multiplication table of this basic central element. So this is that the sum over the conjugacy class of lambda, the sum over the conjugacy class of mu, the product is a certain sum, but these numbers, which are positive integers, are very difficult to compute. There are no real formulas. But for the asymptotics, it turns out that you don't need all of these numbers, but it's enough to sort of look at the degenerate, because not everything, only what you want to know is the contribution only of the leading term of this formula. In particular, you are interested only in the coefficients where nu, where the absolute value of nu is the sum of the absolute value of lambda nu. These are called top connection coefficients. So for example, you take S4 and you have this 4 conjugacy classes, and apart the identity. So the transposition 3 cycles, this product 2 transpositions, this 4 cycle, and you have this multiplication table, and the top coefficients are these ones, which are in box. Okay, and this computation can be done by degenerating the multiplication of the symmetric group. So you just define the new multiplication on the symmetric group by just setting 0 the product of 2 permutations, unless the product of 2 permutations has an absolute value equal to the sum of the 2 absolute values. So this is an obvious way of degenerating the group algebra, which will give you only the top connection coefficients. And then there is a very simple fact, which is basic, that if you take the subgroup of the symmetric group, which preserves the partitions of the cycles of sigma, we have sigma, which decomposes into cycles. Cycles are a partition of the set. You take the subgroup, which preserves this partition, you call it Y sigma. And okay, this is just an example of the, I should have put this before. The main point is that if permutation is the product of some permutation, and the absolute value is the sum of the corresponding absolute value, then each one of these permutations, sigma I, must belong to this subgroup. So this is some kind of reduced decomposition of sigma. The reduced decomposition of sigma is only through elements which belong to the Young subgroup associated to sigma. And then it turns out that inside the degenerate group algebra, the degenerate group algebra of the Young subgroup is the tensor product of the degenerate group algebras of the various symmetric groups of the partition of cycles. And from this, it's not too hard to prove Collins' formula, which maybe I will remind you. This formula here, where this number is just the product of these Catalan numbers. So using the fact that one knows the Catalan number for the full cycle, one can do this computation. Okay, if I have another, do I have another 5 minutes, 10 minutes? Hello?
Yeah, sure. Yes, please.
No,
you can go. You can go on.
Okay. So now I will get back to the more non-commutative algebra sort of picture of this thing. So first of all, one to remind something very well known, but sometimes maybe forgotten, that if you take the alternating skew-symmetric invariants under conjugation of matrices, which means that you want to take the exterior algebra of the dual of matrices and take the invariants under the action of the linear group. I do it over the rational numbers for simplicity. Then this is a Hopf algebra, and by Hopf theorem is a exterior algebra generated by the primitive elements. And the primitive elements are the traces of the standard, of the odd standard polynomials. So this is actually in a paper of Constant, that's one of approaches of Constant to prove the Amitsur-Levitsky theorem. But anyway, this is a standard fact. This is due to Dinking. So you have this appearance of the standard polynomials, of the odd standard polynomials. They have non-zero traces, and these functions are the primitive elements of the Hopf algebra. Of course, the even standard identity, the trace is 0. And then we take the top element of the exterior algebra, which is the exterior product of all the primitive elements. And this is a very simple fact that the multilinear antisymmetric functions of the entire of d squared d by d matrices, matrix variables, is necessarily a multiple of this exterior product. And then there is a fundamental formula. So we take something which, if people are familiar with the Regev polynomial, may recognize. We take this list of monomials. So a monomial in one variable, y1, a monomial in 3 variables, a monomial in 5 variables, and so on. You decompose this square in as 1 plus 3 plus 5 plus 7 and so on. You take these monomials in disjoint variables, and then you alternate all this. You have some kind of an expression, a tensor-valued alternating polynomial. And the main point is that this tensor-valued alternating polynomial is equal to this exterior product of standard polynomials times this Weingarten function. This is essentially hidden in the paper of Formanek. But if you do it this way, the paper of Formanek on the Regev central polynomial becomes much clearer. So, and this is not very hard to show once you understand the formalism of this Weingarten function. So this becomes a fundamental formula, which in fact I used also in a paper with Huber to study alternating tensor identities for matrices. Okay, and then from this you pass to central polynomials, because essentially, okay, here just maybe I can skip this. So you do the same thing, except now I use the variables x instead of y, but because I need both x's and y's in order to construct this Regev polynomial. You take the product of all these monomials and alternate, and then of course this was a conjecture, a construction of Regev, and was the conjecture was that this thing is different from 0. What you know, since it's very easy to prove that it's a scalar, and the multiple of this product, basic stereo product, but it could be 0. And Formanek proves that this is this, and you see that this is actually the value of the Weingarten function, and the reason is actually the simplest explanation is from the previous formula. Let's see if I can give you back the previous formula. From this formula, by using standard fact about the trace of the symmetric group tensor matrices, then you get that the trace of that thing is the trace of this operator is different from 0, and then this gives you the Formanek theorem. Okay, I think this is in fact quite useful in the theory of polynomial identities, since its polynomial satisfies this basic formula, which makes it a canonical element in the conductor of the algebra of generic matrices inside its trace algebra. And no, this maybe we can skip. Maybe I can stop here, unless you want to see a couple more transparencies on Juicy Murphy's elements. So what do you think?
But okay, please go on.
Okay, no, this is just a compliment because this Weingarten function actually has a very nice interpretation in terms of Juicy Murphy's element, which is again a classical construction in the symmetric group. And this is this. So you have in the group algebra of the symmetric group, you define these elements, J sub I, which are the sum of these transpositions. And a simple fact to prove is that these elements commute between each other and generate a maximal semi-simple commutative subalgebra of the symmetric group. And then there is this factorization of this the basic polynomial from which we started, the sum over the symmetric group of the element times d to the number of cycles, can be actually decomposed in this as this canonical factorization. So d times the product from I to k of d plus j I goes from 2 to k. Therefore, the inverse of this is the product of the inverses of these things. These are commuting elements. And then, of course, you can expand each one of the, you have some kind of identity. So from the theory of symmetric functions, you have that this is equal to this. And the inverse is this. Therefore, you see that so this Hj are the total symmetric functions, and these are the elementary symmetric functions. And then you apply this to this factorization here. Instead of xi, you evaluate it in j sub I. And then you get this formula, which is again a complicated formula for the Rhein-Gardner function, is but is a power series in terms of the total symmetric functions of the Juicy-Murphy's elements. But this already has an interesting consequence, which you don't see by the explicit formulas which I gave you. That this thing is greater than 0 if sigma is even and less than 0 if sigma is odd. And this is a formula by Novak, and I can just finish by commenting, by commenting on where this is. So I wrote a note on this unknown journal, which is published by the University of Lecce. And I published there because I was professor at the University of Lecce for maybe 40 years ago, for 1 year. So I decided I would like, I would 45 or whatever. And there is also in archive, there is this abstract, and maybe I have some further references. So this is the paper of Formanek. This is the paper of Juicy's. This is the paper of Collins on where he proves these formulas which I discussed. This is Murphy, and this is Novak. And I think with this, I really finished. Okay, thank you. Sorry for this mess and the death of my computer. That was really a surprise, a bad surprise. Okay, that's it.
Let us thank Professor Procesi for the interesting talk. And then if there are some questions or comments, please. Are there any questions?
No, there's no questions. No question. Okay. We can.
So let us think if there are no questions or comments. Let us thank once again Professor Procesi.
Ok. Questo o non hanno capito niente, o tutto chiaro.
And then
okay.
We have a break. We have a break for some 18 minutes until the next talk. And okay, for the people who are in Sofia, it should be a coffee break. For the remaining, it is also a coffee break, but everyone gets their own coffee. And we resume in 18 minutes. Thank you.
At 4, right? 4.
Recording stopped.
звук еще. Мы видим, что поэтому. Нет, он сам включил. Нам выучить нужно? Нам почти выучить, что надо. Нам структуру выучить. Мы будем вода. Hello? То есть они видят меня, слышат они меня, да? Да. Так, вот, слышит. Так, я вот демонстрацию экран новый сделаю. Сейчас кто-то другой демонстрирует. Hello. Hello.
Hi. People in a coffee break.
Who are you?
I'm Jose Bros. Hi.
Hello.
People is returning from a coffee break now.
Okay. Sorry that I am not able
Hi, Оскар,
to upload video.
Оскар, слышишь меня? Это Миша.
Привет. Привет, Миша. Привет.
Я сейчас ведущий секции, так что через пару минут начнем.
Хорошо.
Ты готов, да?
Я готов. Я прошу извинений, что я не могу показать видео. Я, к сожалению, заболел.
Ну, презентацию ты покажешь хотя бы?
Презентацию покажу, да. Поэтому я не смогу этот...
Ты сейчас дома в Алма-Ате или где-нибудь еще?
Не, я дома.
Ага. Хорошо, Оскар, давай, я буду собирать народ.
Давай.
Even doorgetijd. Even doorgetjes toe.
In front of the computer.
You can sit there.
You can sit there.
So, okay, dear colleagues, it's my pleasure to introduce next speaker now of our conference. Next speaker is Oskar Serkulovich Zumudildaev from Almaty, Kazakhstan. His talk is entitled as Associative Admissible Operator. Okay, Oskar, let's start.
Thank you very much. So this topic is active research topic for me for last several years, and last 2 months I did about 4 talks on this subject, and all times I add something new. First lecture was given in Shirshov conference, then in Shestakov's conference, and now in Drensky conference. And the plan of my talk is the following. So, okay. So I'll give, I remind Computative formula for powers of derivation. Then I remind what is it build polynomials.
Recording in progress.
And I speak about rack partitions, its new notion, and then 3 kinds of multiplication differential operators, and the power of derivation by belt polynomials and by rack partitions. And a new thing that I'd like to speak today, maybe some detailed, series parallel networks and the cographs. Then some applications for Lie admissible operator, associative admissible operator, associatively admissible operator, and so on. And finally, I give cell dual diagram of operands. So main idea here is I construct dimension formula for conditional operands, and this series parallel networks allows us construct another formula, but this differ from the first one is it allows us to construct base of considered operands. So Computative compositions. So a method for calculation of powers of derivations, ADM, is given in this paper. It is Contradu, 1973, page 165 and 168. Call n typal K1 and so on Kn, Computative composition. If K1 is between 0 and 1, K1 plus K2 is between 0 and 2, and so on. And K1 and so on, Kn minus 1 between 0 and n minus 1. Sum of K1, Kn is n. So if Compta n be set of Compta compositions, then takes place the following theorem. So power of derivation can be presented is a sum of differential operators order L. L begins from 1 until n, such that coefficients are the functions from a, dA, and so on, dn minus L, a, and dl. And they are defined by a over L factorial, and here summation made by all Compta compositions. 2k minus k1, 3 minus k1 minus k2, and so on. Example, if we take 0 to 1, so if n is 3, then 3 can be partial. So compositions, Compta compositions of 3 has 5 elements given here, and H31, H32, and H3C can be easily calculated. They are this one, and this one, and hence L cube, so AD integral cube, is linear combination of differential operator first order, second order, and third order. Now I move to another subject. Let A be associative commutative differential algebra generated by generators A0, A1, A2, and so on. Derivation is a linear map that satisfies Leibniz rule. We said dAI is AA plus 1. Then dA is sum of AA plus 1 dAI. I begins from 0. And therefore, dAI alpha is alpha I, A alpha minus epsilon I, AI plus 1. Example, if you consider this polynomial and the dx to this polynomial, then certainly by Leibniz rule, it is equal to this sum of these 3 polynomials. Now, what is the Bell polynomial? If D is A1 plus D, A0 is 1, complete Bell polynomials are defined by B0 is 1, Bm plus 1 is the Bm, M is at least 0. Partial Bell polynomials, BMK, are defined as a part of Bm generated by products of K generators AI. Then Bm plus 1 K is A1 BMK minus 1 plus D BMK. Example, B1 is A1, B11 is A1, B2 is A1 square plus A2, B21 is A2, and B22 is A1 square. If B3 is A1 cube plus 3A1 A2 plus A3, B31 is A3, B32 is this part, and B33 is A1 cube. And the commutatorial meaning of Bell polynomials. Coefficient at A1, L1, and so on, AM, LM is equal to the number of partitions of the set M, 1, 2, and so on, M. the subsets with orders I with multiplicity Li. For example, the coefficient 3 of B32 at A1, A2 means that there are 3 partitions of 3 into 2 parts with 1 and 2 elements. So block 1 contains 1 element, and block 2 contains 2 elements. So 1, 2, 3, 2, 1, 3, 3, 1, 2. Therefore, here coefficient 3. Now extend A by generators B, another generators B0, B1, B2, and so on, and set derivation by A is A plus 1 dAI, dB is BA plus 1 dBi, and D is sum A0 dA plus dB, and we introduce the following polynomials. Z0A is 0, Zm plus 1A is DZMA. Z0B is B0, Zm plus 1B is DZMB. So here we see that these polynomials are. Here we see that until degree 2, it's similar to Bell polynomials. But in degree 3 case, here appears 4 instead of 3. And the degree 4 appears here should be some 11 and so on. So, and if I write similar polynomials for with B, then I obtain the following polynomials. Note that the polynomial ZMA can be obtained from the polynomial ZMB by substitution. B is equal to A. Moreover, polynomial ZMB can be constructed recurrently by polynomial ZKA with help of built polynomials BM. ZMB is BMK, Z0A, Z1A, and so on, Zm minus KA. Here coefficient BK. Here usual built polynomials, but with polynomial ZA. Now, I introduce one notion. I call it Rack partitions. Let Xi be system of subsets. Some of them might be empty, such that I is n, subset of n. Union of Xi is n, and X is at least I for any X belonging to Xi. If Xi is not empty, and Xi intersection Xj is empty if I is not equal to j. So denote by Rn list of Rack partitions of n, by Rn number of Rack partitions. Rn alpha is a list of Rack partitions whose components have type alpha. So define weight of Rack partition alpha by alpha A alpha I index of I. Let omega Rn k is a weight of Rn k. Then theorem is, so that Zka is exactly sum of weights of Rack partitions. So briefly, you can imagine that you have racks, and n books. And books are labeled by 1, 2, 3, 4, and so on, n. And each rack you fill by these books, but one condition that label of books should be no less than label of rack. So if you consider system of subsets and add one more condition that Xi is not empty for all 1 over k, then we obtain usual partition of k. For example, if x1 is 1, 3, x2 is 2, 4, 5, x3 is empty, x4 is empty, x5 is 6, and x6 is empty, gives us Rack partition of 6. So we denote this Rack partition by this way, or by this way. And the list of Rack partitions for n is 2, 1, 2, 1 blocks, and 2 blocks. For n is 3, 1 blocks partition in this one, 2 blocks partition in this one, and here appears 1 special partition that is not a partition. This is Rack partition. This means that second rack is empty. And the third block is in third rack. So for case n, this is here. Altogether, I obtain 24 rack partitions. And let me write them by weights. So one block partition. First block is all blocks at the first rack. Other racks are empty. Then it corresponds A03 because 3 zeros, and A4 because one rack has 4 elements. Second, here I have 2 zeros. It corresponds A0 square, and one block contains only one element, therefore A1, and one block contains 3 elements, therefore A3. And this kind of rack partitions is 7. Therefore, here's 7. And another way, we have 4 blocks. 2 blocks are empty, but non-empty blocks contains each 2 elements. Therefore, here A2 square and A0 square. And I see here 4, coefficient is 4. And for 3 blocks case, I mean 3 blocks non-trivial, then A0 is 1, A1 square is A1 because it's 2 1 blocks parts, and 1 block with 2 elements, therefore A2. And the elements of this count is 11. And finally, 4 blocks partition is A1 4. Therefore, if I take their sum, I obtain the following polynomial. It is exactly polynomial ZKA. Now, for differential polynomial f, denoted by UF, it's umbral. Ideal polynomial that constructed by f with lowering differential powers. I's derivatives AI and the BI are changed to AI and BI respectively. So index are lower. So main theorem here is umbral of A, D, A, and B is Z and B. For example, if AD acts to B, it is AB prime. And if you take umbral, you obtain A0 B1. It is Z1B. AD square B is AD AB prime is AA prime B prime plus A square plus B2 prime. If you take umbral, then you obtain the following polynomial. It is Z2B. And similarly, AD cube B is calculated that so if they umbrals here, you obtain the polynomial Z3B. Now, I introduce 3 kinds of multiplications on differential operators. First one is well known. It is composition of differential operators or multiplication in Veil algebra. So it can be given by binomial coefficient alpha gamma with the gamma V, the alpha plus beta minus gamma. This multiplication is associative. For any xyz, differential n. So this means that the order of differential operator is order of alpha. So in this case, composition is associative. This fact is well known. Second operation is Blake of white operation or circ operation is defined by UD alpha circ V d beta is UD alpha V d beta. And the third one is Blake multiplication or Buffet multiplication or Hadamard multiplication is defined by UD alpha V d beta is just multiply as commutative algebra. And we see that certainly these 2 multiplications, circ and bullet, are not enough to construct this composition of operators, certainly. But as it turned out, it has some interesting properties. So multiplication bullet is associative commutative, it's clear. And multiplication circ is satisfy the following rule. So connection was the bullet and the circ is here. And operation X circ to bullet is as derivation. And here, so X is differential operator first order. So differential operator first order is the same as a vector field. So it acts as a vector field. And if you take two operators as a vector fields, then obtain a left symmetric condition, a so-called Preley condition. And these two properties of these two operations gives us the following theorem. This is let A is differential operator first order. For simplicity, I formulate for one variable, AD. Then an N is Bn bullet L, L circ L, and so on. Example, it can be checked easily. That example, you can check that. So if you calculate these elements in terms of bullet, then you obtain powers of differential operators. And the same can be written as in terms of trees. For example, here L cube is sum of these 4 trees. Here coefficient is 3. And this tree is well known. It is Cohn-Moskowitz tree of degree 4. So in general, if you take a vector field on the line or second line, doesn't matter, then the representation of ln is delta n plus 1. So here all degrees with order in degree 1 correspond to circ, and all degrees with order more than 1 corresponds to bullet. So some particular case, if P is prime, then LP is LP minus 1 circ L plus L bullet P mod P. If you take LP minus 1, it is LP minus 2 circ L plus LP minus 1 and something. And here we obtain some curious property of power of derivations. ADP minus 2 act to A plus DP minus 2 act to AP minus 1 is exactly 0 mod P. Now, dimension sequence for Kochel operands. Let A be Kochel operand. The sequence of components of dual Kochel operand is given by this way. So here, dimensions of Kochel duals, but beginning from 2, and here multiplied by S factorial. Then if you take derivative of Kochel duals, then you can find the lambda I. Then it gives you a formula for recurrent formula for dimension of Kochel operands. So to find a dimension of Kochel operands, you need first find this lambda case. Then if you find this lambda case, it's easy to calculate recurrent way dn. Now another topic, it's cographs. Any cograph may be constructed using the following rules. Any single vertex graph is a cograph. If G is a cograph, so is its complement graph G bar. If G and H are cographs, so is their disjoint union G union H. Example, list of cographs with 4 vertices, corresponding trees, and the multiplicities are given here. So here 10 cographs. This is 4 points, and dual is this is complete graph K4. Here without one edge, here only one edge, and so on. Here multiplicities. For example, here 6 means that you delayed one edge. So this one edge you can select by 6 ways. Here you have delayed 2 edge, but they have no common vertices. You can do that by 3 ways, and so on. And here I can spawn 5 trees. So all of trees has 4 leaves, but they might have multiplicity more than 2, 3, and so on, but no multiplicity 1. And this one has one more characterization. It was done by Riordan and Shannon, 1952. Let be a number of essential series parallel networks and a number of cographs with n vertices. Then generate a function satisfy the following relation. 1xi minus bi is 1 plus ai xi. So bn is 1 over 2 an. A number of cographs Bn is number of essential series parallel networks. So our aim, find not only numbers of cographs, find degree distribution polynomials. It is important for us. Example. So label series parallel networks. So it is series network. It corresponds, if you consider Boolean algebra, it corresponds to product, conjunction. This corresponds to disjunction, and to this series parallel networks, I can present by trees with 3 vertices. So this corresponds to multiplication. This corresponds to addition. So for example, here you can select this kind of 3 ways, because here you can select 3/2, and here is independent. And if you take the sum, you obtain the following sum. D2 is x2 is x61, y1 plus y2. And similar things for n is 4. If you have 4 leaves, then you have here this kind of weights for these trees. For example, here's x3 means that the number of leaves minus 1, and plus means that x. Here, for example, white, but here degree is 3 minus 1 2, therefore y2. Here the degree is 2 minus 1 is 1, therefore x1. And for 2, this means that here should be increasing. And if you add these parallel set networks for n is 4, I see that here I can construct these 12 cases, and this tree has the following form. So this is weighted dimensions of series parallel networks, or weighted dimensions for cographs. So here I give a list of these cographs until for 6. So we can calculate it. Here's D5. And you can know that all of these from 5, all coefficients are divisible by 5. And the D4 is also all divided by 5 except first one. And D6, we say that these coefficients, they are divisible by 7. All of these coefficients except the first and the last one. And here we give the following congruences for weighted dimensions. X pi minus 2 is x pi minus 2 plus y pi minus 2. D pi minus 1 x pi minus 1 plus y pi minus 1, and so on. So if we apply, so why this formula is important? Because these formulas gives us not only formulas for dimensions for free products of operands, they allows us to construct free bases for admissible, for classes of admissible operands. So dimension sequence for Lie admissible operand. Algebra is called Lie admissible. If you take commutator, then you obtain the algebra. Then the class of these algebras has the following dimensions for any n. So this is the dimension of multilinear parts for n. So it is by a Bell polynomial, and mu k is given by this formula. For example, if you would like to construct multilinear Lie admissible base in degree 3, you can do the following thing. It's non-canonic base. Why non-canonic? Because here 2 blocks. Here 4 kinds of trees with 3 leaves, and these blocks corresponds not blocks as before. It is usual multiplication, and this white multiplication corresponds to commutator. It's usual multiplication, and if you so this is Lie multiplication. So this white multiplication corresponds to Lie multiplication. So you obtain that dimension is 11. If canonic base means the following. So here all vertices should be alternative. Here plus, here minus. Plus corresponds to algebra and the Jordan commutator. So base element of this one. Base element this one. But you can see that these 2 bases are equivalent. But this is canonic base. Because all of these basis follows, you can construct this base by this cograph, by cographs. So Lie admissible means that uncommutative is Lie, and the commutative is just uncommutative algebra. How to construct a new base by these two bases? So it is this allows by this serial parallel networks. So dimension sequence for Lie admissible operand. So first 32 dimensions are here. So here is complicated. So here first 11 is 101 and so on. And here last 32. But you can see that from 25, 34 all, ends by 0 or 5. And the theorem here is congruences. If P is at least 2 prime, then the dimension of multilinear parts of Lie admissible operand satisfy the following congruences. D pi minus 1 is 1 mod P, or minus 1 mod P if P is 3. dP is minus 1 mod P, dP plus 1 is minus 1 mod P, dP plus 2 is minus 6, dP plus 3 is minus 56, dP plus 4 is minus 725. It is somehow analog of Ramanujan congruences, but for Lie admissible operand. And some has, yes, one can easily prolong this list and note some interesting properties. For example, dP minus 2 is 1 over 2 modulo P. Another example, if P is 2, then they have a period 7. And the minus 5, minus 1, minus 0 is all are even. And others are odd. And other formulation of this result, if P is 2, then dimension multilinear parts of Lie admissible operand satisfy the following recurrence relation. Ordinary generic function is looks like that. And this sequence for P is 2 has period 7. It generates so-called shift register sequences. And there is several monographs for this subject, especially from Golomb, shift register sequences. It was published in 1967. Then it was republished in about 5 years ago, as I know. So for example, the dimension of Dn is even with probability of 43%, and odd with probability 57%. In particular, number of even dimensions is infinite. Similar number of odd dimensions is infinite also. But this observation is false when you consider distribution dimension congruences Dn for P's more than 2. Probably Dn is divided by 0 if n is more than P squared. For example, Dn is divided by 3, at least n is no less than 9, divided by 5 if n is no less than 24, and divided by 7 if n is no less than 47. For example, all dimensions are is divided by 5. So ends by 0 or 5 beginning 24. Now I remind what is a polynomial identity. So non-associative non-commutative polynomial is called polynomial identity. If you've substituted here elements of algebra, you obtain true statement. And we see that two identities are equivalent if identity, any algebra with identity F satisfy the identity G and vice versa. More general, it is equivalent if varieties are the same. And quasi-equivalence of identities. System of polynomial identities, F1, Fk, G1, and Gl, we call quasi-equivalent if categories of these two varieties as categories are isomorphic. So categories, so this means, example is the following. If F1 Fk is equivalent to G1 Gl, then F1 Fk is equivalent to G1 Gl. Conversion is not true. For example, left symmetric identity is quasi-equivalent to right symmetric identity. But these identities are not equivalent. Now consider co-commutator. So AB plus QBA is called co-commutator. If Q is -1 after Lie commutator, if Q is 1 after Jordan commutator. So it's clear that if S is a class of associative algebras, S-1 considered class of Lie algebras, A plus 1 considered as a class of special Jordan algebras. Note that S-1 forms variety, but S plus 1 is not. Theorem, net Q square is not 1, If C is variety, then CQ is also variety. More exactly, if variety is given by this polynomial identities, then CQs can be generated by F1 minus Q, Fk minus Q. And they are quasi-equivalent with C. So in other words, class of algebra under commutator is quasi-equivalent to original class of algebras if Q square is not 1. So quasi-equivalency has many interesting properties. For example, they don't change solvability, nilpotency, and they doesn't change, for example, simplicity as the dimensions of multilinear parts and so on. Now, here I give commutative trees. Define commutative tree is with non-planar tree. You can permute any branch of a non-planar tree. Number of commutative trees is given by this formula. And here I introduce coloring monoid for in the vertices of trees. So here, so tau q is colored operator. They can be given by the following formula. And if q minus q is equal to this one, therefore it is invertible if q is not plus minus 1. So G1 is commutative monoid with invertible elements. Now Gn direct product of n copies for n-type Q set aleph Q, aleph I don't remember. It's aleph Q is so tau Q1 and tau Qn. So this group is generated by these elements, and I color so binary trees. I color binary trees. And now introduce alpha Liorn elements in free magmatic algebra. So magmatic algebra has base that generated by binary trees. Now I allow to color in the vertices by the group of this aleph, and then I can correspond so-called Liorn elements, because this alpha might be plus minus 1 and so on, and these elements are Lie alpha Liorn element, and I can take a new base of Lie alpha elements. This means that in this case I can construct so-called free products of some algebras, and here I'll say the following: if V is variety without identity of degree 2, then classes of algebras VQ, Q square is not 1, and the V opposite also varieties, and these varieties are quasi-equivalent. And dimension sequences of varieties are equal. So up to equivalence, for example, there are 3 classes of algebras with symmetric or skew-symmetric polynomial identities. So this identity is called alia Q minus. It generated by this polynomial. So this is invertis in is commutator, Lie commutator, and out bracket is usual bracket, out usual multiplication, no brackets. And here Q divided multiplied A commutator BC and so on. And another polynomial is alia Q plus. It is here is plus mean that here Jordan product, and auto product is usual product. And here, like in your Lie case, Jacobian. So then these two classes of algebras are Dn equivalent. So their dimensions are the same. D1 is 1, and Dn is given by the following formula, and lambda k is given by the following way: k factorial by square of 2, and here differences of these two numbers. For example, Dn begins 1, 2, 11, 100, and so on. And one more class is Lie admissible class, alia minus 1 minus. So here 2 operations, 2 brackets in and outer brackets are Lie brackets. They can be calculated by the following formula. And here mu k is k factorial, k minus I plus 1 in degree I divided I factorial. Here 1 to 11, 1, and so on. The difference, so here in first case difference is 100. Here in first case 101. And third class is Just like Jacobian SLE case, but all brackets are Jordan brackets. And here dimensions are 1 to 11, 100, but here difference is in 5's case, 175, here 170. So these three cases are non-equivalent, certainly. So if you consider algebras whose polynomial is symmetric or symmetric, then you can give up to DNA equivalence all of these three classes. I don't know general form at the end. And Alia class 1 is not casual. It's casual, the ones given by this way. And recall that. So I have sometimes or not. So no, let me omit these cases. No, I consider this associative admissible case. So Q square is not 1. Then associative admissible is a variety generated by polynomial identity as minus Q is 1, if Q square is not 1. Then variety as admin Q is quasi-equivalent to the variety of associative algebras. In particular, they are the equivalent, and all of the dimensions are in factorial. No, Q is minus 1. In this case, associative admissible algebra and the commutator is generated by this identity. And it is free product of two operands, com and Lie nil 2. So this satisfies these two identities. And as at minus 1 is casual, and the dimensions is given by the following formula. So here I give dimension for the formula, exponential generated function, and so on. And this casual is given by the following two identities, com R. I call it reverse commutative, ref com, reverse commutative. So this right this way, and then the reverse way, and with this bracketing. So, and here examples of interesting case, quiz 1. So, example case, in this case appears the following interesting examples. Simple algebras are associative admissible. Any anti-commutative algebra is associative admissible. One-sided Leibniz algebra are not Lie admissible, not associative admissible, but two-sided Leibniz algebras are Lie and associative admissible. Any Poisson algebra is Lie admissible and associative admissible. And an algebra with multiplication, EI times EJ is J minus A plus epsilon, A plus J. So if epsilon is 0, it is nothing else as weak algebra. But if epsilon is non-zero, it is new algebra. It is Lie admissible, associative admissible, but not Poisson admissible. It is example of so-called weak Leibniz algebra that I'll introduce some later if I have time. So associative algebras are Lie admissible, but might not be associative admissible. So here a theorem as admissible. Associative algebra is associative admissible under Jordan commutator if only if they satisfy the following identity. Dimensions are 2n minus 1, and then so Cauchy dual is 2n minus 1, n minus 1 factorial. Multilinear by its elements integrand can be generated by elements of this form. It is by permutation Sn such that sigma I is at least I minus 1. And the example of such algebra is Grassmann algebra. Grassmann algebra associative admissible and associative. But we don't know answer to the question on causality of associative admissible associative algebras. It seems that this algebra is casual. In this case, a negative answer will be also interesting. In this case, it gives us an example, natural example of Fauchet causal operands. The example of non-causal operand with the property, this one. So, results of reverse commutative and the anti-reverse commutative operands. Operands reverse commutative, anti-reverse commutative algebras are casual. Any anti-reverse commutative algebra is associative admissible and Lie admissible, and the dual is they concerned by this way, and the reverse commutative is defined by these identities. So here, these two brackets in and outer brackets are different, and the anti-reverse commutative algebra is defined by these identities. Here, two brackets are the same, either Jordan or either Lie. And the base of this algebra can be given by free reverse commutative operand, and in particular, dimensions of this algebra is the following. It is 2 minus 1. Yes.
Your time is almost over.
Okay, so maybe I'll give you last slide, then I'll finish. So associative admissible operands. So it's given by this way. Leibniz algebra operates as admissible, and Leibniz algebra are Cauchy. And associative admissible operand is associative commutative, free product acommutative. And dimension of multiple part of associative admissible operand can be found by the following recurrence relations. It is k factorial, fkn plus 2. It is Fibonacci number. So here you can construct all of this sequence. Here a lot of these kind of properties. And I mean, one more example is associatively admissible operands. So algebra called associatively admissible. If and I plus is associative, and I minus is Lie. So here dimensions given by this way, and it has also interesting property that it generated. One of main example of this algebra is so-called left hook Leibniz and right hook Leibniz identities. So this is multiplied by 2. So example is that any Leibniz algebra is here, and here is the following new non-trivial example. That was not Lie, but it is with Leibniz. And finally, I give you my diagram. So the following diagram is self-dual, associative admissible, associatively admissible, and Poisson operand and weak Leibniz operand. It is the same of Poisson and converse action, and Leibniz operand, Poisson intersection of Poisson with converse action. And this diagram is commutative and self-dual. If we take here Cauchy duals, then, for example, Cauchy dual as admissible is Leibniz. Cauchy dual of this is associatively admissible, and so on. Poisson is self-dual, and weak Leibniz is also self-dual. So here references this one. So thank you for your attention.
Thank you. Thank you very much for your original talk. So many new information. So questions, comments, remarks. Okay, if there are no any questions and remarks, let's thanks again, Oskar. And we have break in 5 minutes. Okay, let's continue. It's my great pleasure to declare the next speaker. Sorry, Luchezar Avramov, University of Nebraska, USA. His talk is entitled Betty Manoit's Overgraded Commutative Rings. Please.
Thank you. So, actually, the title of the talk has changed. So here is an update. I decided to speak on some.
Okay, modification of the title.
That is closer.
Quasi-polynomial growth of minimum three resolutions.
Okay, so I'll be talking about algebra and I'll give a couple of basic constructions we call them.
Увеличи екрана, да.
If we have.
Виждаш. Не, там ще затвориш.
Okay, so if R is any ring and M is, say, a left module, then M is usually not free or anything close to free, but we can approximate it by taking a free module and mapping it onto M. Then there will be a kernel, and we can map a free module F1 onto the kernel of this type and go on, and that would, in general, go beyond the black hole. But this construction here is a sequence of three modules that is called a free resolution of the free resolution of M. And it has the property that the kernel of every map is equal to the image of the map following it, except for the first map who ends with 0 here, and we call this M is isomorphic to the co-kernel of D1. So this is the basic an entry point into assigning to M homological invariants, and one of them would be particularly interesting for me would be if we are given another module N on the same side, so N is another left module, and X type Mn is obtained by applying the home into N at every level. This reverses errors, so we can form Fi. We have a complex like this, and then now the nice property that kernels are equal to images in general is not anymore true. So we have that, but still the kernel in this direction contains the image in this direction. So X type Mn is isomorphic to the kernel of the map del I plus 1 by the kernel of the image of that map. So, and resolution, there are many resolutions. There is a very weak unique extropy for resolutions, but those modules are uniquely defined by those linear groups in general are uniquely defined by M and N. So they are invariants of the pair M and N. Now, although the general situation, we don't have a best resolution in case when R is a local ring, so R will be now local, and this means that it has a unique maximal idea of N, and R mod N is a division ring. So we'll call this A. So when R is a local ring and allows suppose that it's Euclidean, or grade non-negatively graded link, again Euclidean, then there is and n is finitely generated. Then there is a unique upwise-Norton resolution such that the every differential maps di of fi is contained in n times f1. So, and in this case, we say that the ranks of these modules, so beta I of n is defined to be the rank of fi in the minimal resolution. The k rank of the R rank of fi. And it turns out what can be easily seen from this definition, this condition, then it's actually equal to the dimension as k vector space. So we have a division of this, so it's dimension in k vector space of xi and k. So this is where one starts. And so this gives us an potentially infinite sequence of integers, and I'm interested in the sequence bin. So, and especially in its asymptotic behavior, or how does it grow? One can ask all kinds of questions, and such sequences have been very intensely studied, especially in these two situations where from now on R is commutative. So what I want to illustrate is how non-commutative algebra comes in solutions of questions about commutative rings and their modules, and non-commutative in general, not even finitely generated algebras appear, but I'll soon come to a situation where we're looking at non-commutative but Euclidean algebras which are actually Hopf algebras and universal developing algebras of the algebras. So that's what I want to talk about. And the example, and this example you can take as a definition, because it covers many important cases. So we can think about R as being a power series rings in finitely many indeterminates, factored out by some idea of I. And we can also assume that I is contained in the square of the idea generated by the indeterminates. So that's not all local rings are like this, but if the local ring happens to be an algebra of some field, then we can replace it by a ring of this type. And of course, when R is graded, we can assume that it is equal to it has this form, and I now is homogeneous. So it is generated by forms of various degrees, but and I will assume that all the degrees of the excites are equal to 1. So that's the standard plane of the polynomials. Once we have this, in those situations, there are a number of results is known about the behavior of the bed numbers, but I want to start with a dichotomy, namely there are two possibilities. One is that the sequence behind of M is bounded above by some polynomial in I. So every beta number is the same polynomial for all i's, of course. And or there exists a constant bigger than 1 such that beta I of M is bigger or equal to C and CTBI. So either it is a polynomially bounded sequence or for every modular. So for every M, one of these two conditions for two cases occurs. So that I'll give references later on. I want to state a couple more results. So this situation, in this situation, we have, so that's the general situation where the growth is eventually polynomial. But in this situation, we have more information, and here is a theorem that goes back to Bullison in 1976, which says that well, there are other things that other people, but one, so beta I M is bounded by a polynomial, is polynomially bounded. For OM, if and only beta I M is given by is equal to some quasi-polynomial of degree of period 2 for OM. For all I bigger enough. So a quasi-polynomial is a polynomial, quasi-polynomial period 2 is a polynomial whose coefficients are periodic functions of period 2. So just polynomial bounds implies this specific kind of growth, but this is for OM. This solve is for OM, and it's even only beta I of K of the residue is given by a polynomial. Now, real polynomial, and also for beta. And if and only R has, and I'm now giving the definition in the example. So if R is equal to a quotient of a power series ring, or I don't know, by a sequence generated by forms, by series without constant or linear term, and such that Fj is a non-zero divisor on F1 for J through C. So this special kind, this strong condition of yes. So the first F1 is of course not zero divisor because we are in a domain, but already the second one means that they have no common factor because it's a factorial domain, but after that it becomes a more complicated condition, but it is a very strong condition. So such a sequence is called, such a sequence of elements is called a regular sequence. And so the definition is that R is complete intersection. This is one of the definitions. If it has that one. Okay, so now we know that polynomial, quasi-polynomial growth occurs only for complete intersections, and that it only occurs for but we don't know what kind of quasi-polynomial growths can occur. So the question is, and I'll put it first in when is each n, when does each n have polynomial growths. And when so when do all n get polynomial growths? So quasi-polynomial degree period 0, period 1. And for this we have a complete answer is in the graded case. So if R is graded, each n is polynomial growth. If and only C minus 1, if, of course, we need complete intersection, there's no say, and C minus 1 FIs have degree 2. So we have C minus 1 quadratic forms, and the last one can be a very degree. So this direction I put in 1992, and that's whether the converse holds, and the converse was recently proved in joint work with Zheng Yang, who was a graduate student, and Alexander Sofia, my colleague in England. So this is not such a going in that direction. Going in that direction, one uses Let me just say that use so in the local case we don't know the result, we don't know the complete answer. We know necessary and sufficient conditions which are not necessarily the same, but if yes, codimension it is in this case. So if E minus C is more equal to 3, or E minus C is equal to 4 and K is algebraically closed, then also will follow. We don't know the answer in the local case, in general for the local case. So for quasi-complete intersections, for quasi-polynomial groups, I'll sketch the proof of the key of one key result. And that's where the non-commutative algebra comes in. So here is a theorem that we have it uses the associated gradient ring effect. This is some calculations by the maximum ideals of R. So this is a gradient ring, and as a gradient ring is equal to kx1 xe factored out by some ideal j, and let we can put the nice notion that I square be the ideal generated by the quadratic forms the ideal in this gradient ring. So this ideal contains it's generated by quadratic forms. So let H be the maximal number of forms in I2, such that that form. So this is a maximal number of in the forms in I2 star is the same, such that form a regular sequence. So then every RW has the summation vi and zi, this form of our series, which is called the Congress series of the model. This is equal to some polynomial in C divided by 1 minus z to the power c times 1 plus z to the power d, where d is at most c minus h minus 1. So this is equivalent to saying that just by partial fraction decomposition, this is equivalent to saying that the Poincare series, the petty numbers are given by quasi-polynomials of degree at most c, and one for the even numbers, one for the odd numbers. So for the one for the even petty numbers, one for the odd petty numbers. And so there are two quasi-polynomials, and that these polynomials coincide from the highest d terms of these polynomials coincide. They are the same. So the polynomials have an overlap that is measured by those steps. So how much do I have? 5 minutes or what? Okay, thank you. So this is the proof of this result comes to schedule 2. I explained what X star and K is, but this sequence of gradient vector spaces. But if we take the direct sum, this is a gradient module over X star, the direct sum of X star R K K, which is a gradient algebra. So that's just general homological algebra. Just for any R, any M, any K that works. And such that now we are in the situation, the Newtonian local gradient situation, such that let me call this curly M and this curly R, just for the show, such that M is finitely generated over R. That's actually Bullich's theorem that I quoted earlier, and R is now I'm in the situation of local complete intersection. So R is complete intersection, and R is the universal invariant algebra of a gradient V algebra, such that pi star of R is 0 for I different from 1. So if you gradient Lie superalgebra, it's a Lie superalgebra, but Z gradient or N gradient, and so what because we have only this is no characteristics, but in characteristic the definition of Lie superalgebra is of course the same as Lie algebra, except that if you commute elements A and B, then you have -1 to the degree of A to the B, that's the degree of A, and the Jacobian identity gets also weighted by -1. So that's all there is to Lie superalgebra, except that there are additional axioms. The characteristic K is true. So because we are only meaning 2 degrees. Actually, what in this situation, what this says is that we have a quadratic map from pi1 to pi2. That's the same, that's equivalent to having a quadratic map, let's call it kappa. And this is a fairly simple structure. The problem is how to relate this structure to this quadratic map, how to relate it to the structure of the R. And the theorem is that with C and H, as I defined before, namely the codimension of the R and the quadratic codimension. The theorem is that the linear that pi star of R contains a algebra that are called lambda star, and the quotient is an abelian algebra. So let's call it alpha star. So there is an exact sequence of the algebras, super algebras, like this, such that alpha I is 0 for I different from 2, and lambda star and pi. There is an exact sequence like this. So you have a real algebra constant here, and the other thing is that the universal empirical algebra of lambda star is a triangle dimension. This means that every resolution over this universal empirical algebra is has zeros at some point. Once you have this, there are standard, well, more or less standard results from homological algebra. That first of all, they tell you pi star is finite dimensional. This is the universal enveloping algebra here is Vesselin, and the universal enveloping algebra pi star is free over that of L star by the Poincaré of Witt theorem for superalgebras. And there are standard results that give you as a corollary that because every algebra over an universal enveloping algebra that has that comes from such an extension, the corollary is that the M, the dimension K and I, Zi is equal to 1 to something polynomial divided by 1 plus t, 1 minus c, 1 plus t times to the c minus h. So we are one short here to what we claimed, but there are some additional homological things that work to get us that this polynomial is divisible by 1 plus t and to get us to the final assumption. So the result that I stated is best for is optimal in the sense that they always that they are for each pair of C and H. So H is smaller or equal than C. Well, actually, it's smaller than C. For each pair H smaller than C, there exists a ring and a module that have exactly those poles, those order the poles. we don't know if this is always true. If given an algebra with these parameters C and H, that over the given ring R, we can construct a module of with such Poincare series. But that's hopefully for some other book. Thanks.
That's it. Please, questions, comments, remarks to this talk? So, okay, if there are nothing else, let's thanks again. So we have 14 minutes break.
Primeiro, imagine нещо vacuum и какво правиш рационално си разделен. Да, има ли случай, когато
Hello, just to make sure, my talk starts at 5:40. Is this correct? Hello. Hello, hello. Shall I start?
Okay, just a moment. I will introduce you. Our next speaker is Tatiana Katyeva-Ivanova, American University of Bulgaria and Institute of Mathematics and Informatics from Bulgarian Academy of Sciences. Talk is entitled Algebras Defined by Linden Words and Artin-Shelter Regularity. Please.
Okay, hello everybody. It is a pleasure to talk on this conference. I want to express my best wishes to Vesselin Drensky, with whom we are friends since, not only colleagues, since many years. Today, I shall speak about algebras defined by Linden words and Artin-Shelter regularity. All algebras in the talk will be considered over a fixed field K. We shall consider initially associative algebras, and then we shall switch to Lie algebras and their universal enveloping. First, I will remind the definitions of Artin-Shelter regular algebras, and then explain the main settings, and then I'll come to the main result. A connected graded algebra A over a field K is Artin-Shelter regular if, first, A has finite global dimension D. That is, each graded A module has a free resolution of length at most D, but at least one of the modules has a free resolution of length D. A has finite Gelfand-Kirov dimension or polynomial growth, second property. And third property, A is Gorenstein. In the non-commutative case, that means that xi A, Ka is 0 whenever I is different from D. We speak about global dimension D. And x dA Ka is isomorphic to the field. Artin-Shelter regular algebras were introduced and studied first in the 90s. The pioneering paper was by Artin-Shelter, and then classification of such algebras, of all algebras of global dimension 3 and other properties were given in the two papers by Artin, Tate, and Vandenberg. The problems of classification and finding new classes of Artin-Shelter regular algebras are central for non-commutative algebraic geometry. When the global dimension is at most 3, all regular algebras are classified. The problems of classification are difficult and remains open even for regular algebras of global dimension 5. But of course, many papers appeared and a lot is known. My approach will be combinatorial. Let me put the settings. We have a finite alphabet X with n elements. W is an anti-chain of monomials in the free semigroup. And what we study are not just particular algebras, but classes of algebras, in fact, of associative graded K algebras, which are generated by X and have a fixed abstraction set W. I shall give brief description what means abstraction set, but those who know Grobner basis theory, this is the set of all leading monomials of the unique reduced Grobner basis of the ideal I. Our study is related to the following questions at least. A classical combinatorial problem in algebra, the study of algebraic objects presented via generators and relations. The main question we investigate is when a given class, so for the class, we only know the set of abstractions. When such a class contains a standard finitely presented Artin-Shelter regular algebra. There is an open question, still open. If a finitely generated K algebra has polynomial growth and finite global dimension, is it true that the degree of the polynomial growth and the global dimension are equal? In all algebras that we study, we prove that for them, this equality holds. This is true whenever the monomial algebra, every such a class has a unique monomial algebra whose ideal is generated just by W. So this is equality is true whenever the monomial algebra has finite global dimension. Some brief reminder of definitions and conventions. So on the free monoid, in fact, on the free semigroup, we consider the pure lexicographic ordering. It is not compatible with multiplication from the right. This will be needed for the definition of the Linden words. But every information related to Grobner basis, for this, we consider the degree lexicographic ordering on the free monoid. Keep in mind, we order, although we shall not use this explicitly, but I have to explain, our degree lexicographic ordering is induced by this order of the generators. So all Grobner bases of associative ideals in the free associative algebra, and all Linden-Kirchhoff-Lie bases of Lie ideals in the free Lie algebra will be considered with respect to the degree lexicographic ordering on the free monoid. Now, I just want to say briefly what means anti-chain of monomials. This is a formal definition, but you can easily imagine a non-formal definition. Anti-chain of monomials means a set of monomials such that if you take two arbitrary monomials there, no one of them is a proper subword of the second. But here I just give a partial ordering which explains this. So we say that I is less than B if A is a proper subword of B, that is B has a greater length and such presentation. A set of words is an anti-chain of monomials if no two elements of W are comparable with respect to this ordering. Having an anti-chain, we can define what means a normal word modulo this anti-chain or standard, W standard. The word A is normal if it is not divisible by any of the elements of the anti-chain W. And we consider the set of all W normal monomials. It is closed undertaking subwords. If a word is normal and you take a subword, then this subword is also normal. Now, how W appears in the context of an arbitrary ideal in the free associative algebra? We take the set of all highest monomials of elements in I with respect to the degree lexicographic ordering. And the set of abstractions for this ideal is the subset of all words in W bar which are minimal. That means it is explained as a set. In fact, W is the unique maximal anti-chain of monomials. So it is maximal. There are no larger. Of course, if we have fixed the ordering as we have done already, W depends only on the ideal I. It is invariant of the ideal. Let A be, it is a typical presentation of a finitely generated associative algebra. The theory of Grosvenor bases implies that there is an isomorphism of K vector spaces. Kx is a direct sum of the span of the normal words plus I. And as a vector space, A is isomorphic to the span of the normal words, and the set of normal words is a K basis for A. We shall work with this K basis. W is called the set of abstraction for N, or the set of abstraction for A, to simplify terminology. Here I give an example to show that a class may have very different algebras sharing the same set of abstractions. Take the quadratic algebra. This is an algebra with cubic relations to defining relations of degree 3, homogeneous. There, one can check that this set is the reduced Grosvenor basis of the ideal I generated by F1 and F2. And then the set of abstractions is exactly as it is written here, XXY, XYY. And these are the first interesting examples of Linden words in alphabet of 2 elements. The K basis is Poincaré-Birchow-Witt type of basis. This algebra is an example of an Artin-Shelter regular algebra of global dimension 3, type A. It appears in the first paper by Artin and Shelter. Another algebra in the same class. This is the universal enveloping of the 3-dimensional Heisenberg algebra. Here, I present it as a monomial Lie algebra defined by 2 Lie monomials, namely the standard bracketing of XX and Y. Here it is given, and then I present it as associative element and the standard bracketing of X, Y, Y. Again, one can check that this is the reduced Grosvenor basis of the ideal I. But if you take just the standard bracketings as Lie monomials, this is a Grosvenor basis, Grosvenor-Kirchhoff-Lie basis of the Lie ideal. I don't want to go into detail, just to give you some flavor. The algebra is the enveloping algebra of the three-dimensional Lie algebra. And it is known that every enveloping algebra of a graded Lie algebra, which is finite dimensional, it is Artin-Shelter algebra of global dimension, the equal to the dimension of the Lie algebra. This is just for information. First results. Given the class XW such that the monomial algebra has finite global dimension and finite Gelfand-Kirchhoff dimension, then it is a not a result of mine, then these two are equal and every algebra in the class share the same global dimension. Typically, a typical algebra in the general case would have global dimension bounded from above by the global dimension of the monomial algebra. Here we have a bound for the number of defining relations, that is the order of the abstraction set. It is exactly bounded by D choose to. This is part of the main, one of the main results. And very interesting things happen if we have equality. This will be explained in the theorem. Here I have written. I skip. Now I come to the first result, which is formulated for an arbitrary class CXW. W is the set of abstraction, where W is an anti-chain of monomials. So what is our hypothesis? We assume that the monomial algebra has polynomial growth and global dimension D. When W is finite, these two properties can be algorithmically checked. Let A be an arbitrary algebra in the class. Then the global dimension of A equals D equals it Gelfand-Kirchhoff dimension. By the way, I want to remind that all algebras in the class share the same K basis, the set of all normal words modulo W. So the surprising thing is not about the Gelfand-Kirchhoff dimension. It is the same as the Gelfand-Kirchhoff dimension of the monomial algebra, but that the global, it's not surprising anymore, but it was proven a long time ago by me that the global dimension of A must be equal. This is follows from Anik's works. There exists a finite set of normal words called atoms in the sense of Anik. Exactly D atoms. These are normal words. The alphabet itself is a normal, such that the normal K basis of arbitrary algebra in the class has this Poincare-Birchowitz type property. And so the atoms here, we don't have the generators themselves, but the atoms, some of them are also generated. The Hilbert series is called correct Hilbert series, the same as the commutative polynomial ring with degenerators of certain degree. The abstractions, every abstraction has this shape, but not all monomials of this shape participate in W. But this already gives an upper bound for the number, for the order of W. So A is standard finitely presented. The ideal has a finite reduced Grobner basis R of cardinality of order at most D choose 2. This bound is exact. The following conditions are equivalent, and each of these conditions explains that there is, up to isomorphism of monomial algebras, there is unique such a class for which W has order exactly D choose 2. So the following conditions are equivalent. The set of abstractions has D choose 2 elements. D is exactly the cardinality of the alphabet, our N. The Grobner basis is quadratic. This means PBW algebra in the sense of 3D, not concurrable with as we can expect. The set of atoms is exactly X, and there exists a possible new ordering on X, so that the set of abstractions consists of all possible monomials of length 2, satisfying this condition. In fact, in this case, we shall see that, in this case, W is already a set of Linden words, and we shall see that in this case, the class, in the extreme case, the class contains many Artin-Shelter regular algebras, quadratic algebras, which are related to Young-Baxter equation, etc., but I don't want to go to these details. The algebra, every algebra in the class under the assumption, the extreme assumption, is causal. From now on, we concentrate only on anti-chain of Linden words. This is one of the open questions which I formulated in a conference in Bedlevo when I spoke about monomial algebras defined by Linden words, but there were some reasons to ask it. Is it true that if A is a standard finally presented Artin-Shelter algebra, a regular algebra, there exists an appropriate ordering on X so that the abstraction set of A consists of Linden words? In fact, we don't know yet Artin-Shelter algebra, which is given with their precise relations, standard finitely presented algebras, for which this is not so. All algebras that are known so far give positive answer. In particular, this is true for the class of Z2 graded Artin-Shelter regular algebras of global dimension 5. They were classified by Floistad and Watney. Now I remind briefly what is Linden word. You cannot remember this just from this talk, so it is a reason to look in, for example, in the good book of Voltaire. I take the classical Western definition of Linden words. There are analogous notions such as shop words, but I prefer to keep the name Linden words because I use only this definition. So Linden word in the alphabet, X, is every word which is minimal in its conjugate class. That means if it's written in arbitrary way as a product of two monomial, and you take, instead of AB, you take the monomial BA, U is always less lexicographically than BA. The set of all Linden words will be noted by L. By definition, every letter from the alphabet is a Linden word. And here I give a list of all Linden words of length at most 5 in the alphabet X, Y, where X is assumed to be less than Y. I shall remind something important, that if we have a Linden word, the right longest proper segment of W, which is a Linden word, let it be B, then what remains, the other word A is also a Linden word. And this is used to define inductively the standard bracketing. I shall skip this, so I assume the listeners know many of the notions that I use because the talk is relatively short. So with each abstraction set W, which consists with each anti-chain of Linden words, we associate another set called Linden atoms. It is uniquely determined. These are the Linden words that are normal modulo W. And N is essential. So knowing set N of Linden words which satisfy certain property, you can immediately restore the set of abstractions in the other way around. So here, these are the properties of the set of Linden atoms. The Linden atoms, if W is fixed, contain the alphabet, and together with every Linden atom, every proper Linden subword must sit there. And having a set with these properties, C1 and C2, we can immediately define uniquely the set of abstractions. So we call Wn a Linden pair. Our classification and many of our results will be in terms of Linden pairs. So there is a duality, knowing. So here we come to another important open question. Let N and W be a Linden pair when the class CXW contains an Artin-Shelter regular algebra. If yes, then N must be finite just because of the polynomial growth. N has order D if the algebra, if N has order D, then we already know that the order of W is bounded, but this of course is not sufficient. Another thing that we know is CXW contains an abundance of Artin-Shelter regular algebras whenever W has exactly these two elements. Here, N must be X. The global dimension of each such algebra is N, and you'll see theorem B. In this case, the class contains more than 2,400 Artin-Shelter regular algebras, which are related to the skew polynomial rings I introduced long time ago, and to the Young-Baxter equation. And CXW contains at least one Artin-Shelter algebra whenever W has order exactly D minus 1. This is the lower possible bound. N should be also connected. This has to be explained. So we answer this in theorem C. But there are classes which, for sure, no matter that they are defined with set of abstraction consisting of Linden words, there are classes which do not contain Artin-Shelter regular algebras. So the first exceptional case was given in a joint paper with Floystat. The monomial Fibonacci-Linden algebra cannot deform to Artin-Shelter regular algebra. This is just for completeness. I skip. Now, what means connected set of Linden words? Connected means that if the set has a Lindenwert of degree m, of length m, then for any integer smaller than m, say s, there should be at least one Lindenwert in n of length s. This comes from the Lie algebras property. It is all this talk is part of a paper that will appear in Transactions of the American Math Society this year. And this being connected is a sufficient condition if the class the class CXW contains the enveloping algebra of a Lie algebra G, then it must be connected. And the bracketing of n is a k-basis for G. Now we come to the second result, which already refers to classes in which the set of abstraction is an anti-chain Lindenwerts. Let W be an, so first we start, just to give a flavor, arbitrary anti-chain, but we want to see when this anti-chain must be anti-chain of monomials. So this is a neutral definition, anti-chain of monomials. We take the set of all normal Lindenwerts modulo W. This does not need to be necessarily finite. Then W is an anti-chain of Lindenwerts if and only if the set of normal monomials has this classical shape. Of course, here we may have this S is not bounded, so it behaves like Poincaré for it. Now, suppose from now on that W is an anti-chain of Lindenwerts, and let A be an algebra in this class. Then the Gelfand-Kirchhoff dimension of A is D if and only if the set of Linden atoms has exactly D elements. This is transparent from this basis. And in this case, the following conditions hold. The global dimension of A is D. Also, the Hilbert series is the proper Hilbert series. A is standard finitely presented with cardinality of W bounded from above, as we already know, by D choose 2, and from below by D minus 1, and these bounds are exact. And the class contains Artin-Shelter regular algebras anytime when W is either D choose 2, this is not a surprise, or W has order exactly D minus 1 and n is connected. In this case, the class contains the universal of the filiform algebra. So this is more general view. And now the next theorem just explains a sufficient condition. This is not a main result, but gives some light. If we have a Lie algebra and use the enveloping algebra, then the set n is connected. AF, the monomial algebra, AW is a monomial algebra defined by Lindenwert in the sense of the paper of joint paper with Foystat. And if J is generated by homogeneous Lie elements, then both U and AW are in the class, and the following conditions are equivalent. U is an Artin-Shelter regular algebra of global dimension D and has exactly D elements. The dimension of the Lie algebra is exactly D. The Gelfand-Kirov dimension of U is D. And each of these equivalent conditions implies that U is standard finitely presented, and this inequality holds. Now we come, this is more essential, the other just gives a flavor. If we have, what happens on the boundary? This is the answered by, by theorem C. If N has exactly D elements, the following are equivalent. W has order D minus 1, and 10 is a connected set of Linden atoms. X must be an alphabet in just 2 elements. This is the motivation for our classification. And up to isomorphism of monomial algebras, the atoms are just of this shape. You may recognize that the standard bracketing of these elements are the basis of the filiform Lie algebra. And these are the relations if you take the brackets of the filiform Lie algebra. In this case, the class contains the universal enveloping of the filiform Lie algebra of dimension D and nilpotency class D minus 1. And this a regular algebra with global dimension D. For the second boundary, I shall skip because I made a comment in the case when when W has exactly D equals to elements, again the class is unique up to isomorphism of monomial algebras. Of course, there are many algebras there, but the class is unique. Now, I will briefly define what means monomial algebra. We take an ideal generated by the standard bracketing of the monomials in W. And we consider the Lie algebra. Lie algebra module J is called monomial algebra, defined by Linden words. And it is called a standard monomial Lie algebra if the standard bracketing of W is a Grobner-Kirchhoff-Lie basis of the Lie ideal J. In this case, its universal enveloping algebra is in the class. And the question that we are interested is to classify the Linden pairs such that the class contains the enveloping algebra of a concrete monomial Lie algebra for, of course, this is a not trivial problem, but we may start with concrete, we may start upgrading the cases of the order of N. So here is the theorem. No, this is the main, not the main result, but just to give you idea that importantly algebras have presentation as standard monomial Lie algebra. For example, each of the, this is a theorem in the paper, each of the classical filiform algebras, the filiform algebra of dimension D plus 1, and so there are two when D is solved. Each of them is a monomial algebra. I want to come to the last theorem, the classification. So the most, I don't say easy, but the first thing to try to do is to classify the Artin-Shelter regular algebras that occur as universal enveloping of monomial algebras in alphabet of 2 elements. When N is 6, this means the dimension of the Lie algebra is 6. in fact, we classify in terms of Linden pairs. There are 8 Linden pairs, but only 4 of them give the algebras under request, and I'll end up with the list. When n is 7, there are in general 30 Linden pairs. We classify first the Linden pairs, and then we study only 9 of them. The first are give Artin-Shelter regular algebras occurring as universal enveloping algebra. Some of these classes do not contain universal algebras at all, just because the sets are disconnected, and the open question is only about 3. And here are the exact moment, and I end. So these are the pairs, they're written explicitly, for which we have global dimension 6, Artin-Shelter regular algebras of global dimension 6, but they occur as universal enveloping. The second 2, the third and the fourth are filiformly algebras of dimension 6. Of course, you have to take standard bracketing. And these are the first 9 are explicitly given. If you know the set of atoms, you can write explicitly the set of relations. The set of abstractions, take the standard bracketing, and that's it. To do this, so the open question is only for those 3 algebras. The question is, no, the corresponding monomial algebra is not in this class, but maybe the class contains other Lie algebras with this set as basis. So this is open, and these are huge, so these are many, all remaining which do not contain universal Lie algebra at all, because they are disconnected. And that is the end. So imagine a slide saying thank you. And that's the end of the talk.
That's it. Thank you very much. Is there any questions to Tatiana?
Just one remark, maybe. Thank you for the nice talk. There was mentioned one problem, that is whether there exists an algebra whose global dimension is greater than the number of generators. I'd like to mention that now this problem is solved negatively because of a paper by Yudo and Shkarin. They have classified the 3 generated Koszul algebras and found a Koszul algebra with 3 generators of global dimension 4. Of course, this algebra is very far from being Artin-Shelter regular. So for them, this is, I think, the open question.
But the very first result that in fact, even here, I shall admit, the reason I came to Lindenworth was that there was a very nice conference in Isle of Skye, and there I met personally Gunnar Floystad. And he asked me, can I construct algebras with just 2 generators and as great Gelfand-Kirov dimension as we want? And I started building such algebras. I even have forgotten Lindenworth. I was just building such algebras intuitively on alphabet of X and Y. And he said, so the idea was finite global dimension and polynomial growth as far as large as we wish. And I used this Anik idea of n-chains, and Gunnar said, but these are Linden words. And then I started reminding, I was lucky then I was free of teaching, And I was in Bonn and started reading like crazy the book on Lindenwurz by Luther. And then the first thing that we did was to study monomial algebras of finite global dimension and polynomial growth. And general results are done. Of course, we studied monomial algebras defined by Lindenwurz. And the reason is Lindenwurz have extremely nice combinatorial properties. And then we describe some concrete results for, but this is just as application for alphabet of 2 elements. So of course we can have as large global dimension as we want, but the polynomial growth must have the same degree. In general, if we work with standard finitely presented algebras of finite global dimension, the global dimension of an algebra in the class is bounded from above by the global dimension of the monomial. I don't know, did I say something in connection with your remark? Anyway.
Okay, yes, thank you. Yes.
So it is not clear, are these always equal? The global dimension, providing they are both finite. That it is not clear. I mean, I don't think that still there is an example negative. Okay, so.
Okay, thank you, Jake.
Thank you for your answer. More questions? Maybe some remarks, some comments. Okay, if there are no more comments and remarks and answers, we declare the break in 13 minutes.
Okay, so I stop share. I stop share. I see you again. And it's nice to see you all virtually. So till our bye-bye. So I mute myself.
Okay, let's begin with the last session for today. The first talk will be given by Tiago Castillo de Mello. It is entitled The Commutative Degree of a Polynomial and Images of Multilinear Polynomials. Please.
Everyone can see?
Yes, at least here it is visible.
Okay. May I start?
Yes, please.
Thank you. So first I'd like to thank the organizers for the opportunity to give this talk here. And also I'd like to congratulate Professor Drensky for his anniversary. This is a joint work with Ivan Gonzalez from Technological Federal University of Paraná in Brazil. And we're going to talk about the commutator degree of a polynomial and image of multilinear polynomials. The idea here is to give a solution for the problem of image of multilinear polynomials on the algebra of upper triangular matrices. Okay, that we are going to denote by UTN. And to that, we are going to introduce the commutator degree, which is a combinatorial tool to handle with this problem. Okay. First, we start with the definition of the image of a polynomial. So we are considering here the free associative algebra, okay, and a polynomial will be an element of it. So a polynomial here, I mean a polynomial in non-commutative variables. If you have a polynomial in m variables, it defines a map. It defines a map here from the n copies of k by k matrices to the algebra itself by evaluating the variables by matrices from this algebra of k by k matrices. Okay, so the question which is attributed to Kaplansky is which subsets of k by k matrices can be considered as which subsets are images of some polynomial in Fx. Okay. Actually, here you can consider a more general question instead of considering the algebra of matrices. You can consider an algebra A. And you have this, right? Actually, it doesn't need to be associative. If you change here your polynomials, if you consider non-associative polynomials, you can consider the problem of image of polynomials on non-associative algebras too. Okay. Well, let's see some examples. The first example is this polynomial, and it's very simple to see that its image is the whole algebra. Okay. If you consider the standard polynomial of degree 2k, which is defined here, but I believe everyone here knows it, we know by the Amitrud-Levitsky theorem that its image is 0. That is, it's a polynomial identity for k by k matrices. Also, another important result here is when you consider the commutator. It was proved by Schoda, and later by Schoda in characteristic 0, and later by Albert and Muckenhaupt for arbitrary characteristic, that the image of the commutator is the set of trace 0 matrices. Okay, so any trace 0 matrix is the commutator of two matrices, x1 and x2. And finally, this last example says that this polynomial on 2 by 2 matrices has image equals to f. Here f is representing the set of scalar matrices. Okay. Actually, we are saying we are saying that this polynomial is a central polynomial, and this is an identity. So in the language of multilinear the language of image of polynomials, the ideas of polynomial identities and central polynomials are always present here. Okay, let's see what can we say about the structure of the image of a polynomial. So the first thing we are going to note here is that the image of a polynomial is invariant under conjugation. Okay, so if you consider a polynomial f, we are going to evaluate on a set of matrices here, and we are going to perform this operation. We need to show that this is still an element of the image. It's simple to see because this guy here is a linear combination of elements of this type, right? So if you multiply on the left by this, on the right by this, you are obtaining this, and so on, right? So this means that this equals to the polynomial f evaluated on these elements here. So the image of polynomial is a set which is invariant under conjugation by invertible matrices. What else can we say about this set about the image of a polynomial? If the polynomial is multilinear, it's closed under scalar multiplication. It's really simple to observe this. Actually, we have a more general result for homogeneous polynomials, but I'm not presenting it here. And we can ask if the sum of two elements in the image is also an element of an element in the image. So actually, this is the question of Lvov that asks if the image of a multilinear polynomial over a field is a vector subspace. Okay, it seems a naive question, but we only have a solution for 2 by 2 matrices in this case. Okay, since we are trying to understand if the image of a polynomial is a vector space, let's see what can we say about the linear span of the image of a polynomial, right? So the first result here is that the linear span of image of a polynomial is a Lie ideal, okay, which is an ideal. Sorry, not an ideal, but it's closed under brackets, okay, the brackets, commutators by arbitrary elements. But there is a classification when we are working on infinite fields for the Lie ideals of k by k matrices. There are only 4 possibilities, which are these 4 here. So with this, we get this corollary that says that linear span of the image of a polynomial is one of the 4 subsets here. Okay, you can see that these 4 subsets are exactly the ones I give in the examples here, right? Well, and this is the now known as Lvov-Kaplansky conjecture, that if f is a multilinear polynomial, then its image is one of the 4 possibilities here. 0, when we are considering a polynomial identity, f, when we are considering a central polynomial, SLK or MK. Here, we mean the traceless matrix, right? An interesting fact here is that this has dimension 0, this has dimension 1, this has codimension 0, this has codimension 1. That means the possibilities here are or too small or too big. Okay, these are the only possibilities, and this is the conjecture. Before seeing the known results about this conjecture, let's see an example that if you consider non-multilinear polynomials, the conjecture is not true. Okay, so we are considering here k by k matrices and considering the polynomial x to the k, one variable polynomial. Okay, let's evaluate it on the set of some matrix units here. Okay, everyone knows here this matrix means that matrix with 1 in the entry ij and 0 elsewhere. So evaluating on EII, we obtain itself. Evaluating it on this, we also obtain this. So if these 2 lies in the image, their difference lies in this subspace generated by the image, the linear span of the image. So we obtain that in the linear span all of these elements are, so the linear span of the image is the whole algebra. Okay? And now we are going to show that the span, not the linear span, but the image is not the whole algebra. So let us assume that this matrix lies in the image. So there is a matrix A for which it satisfies this condition. Okay? But this is an important matrix if I is different from J. Since it's an important matrix, some power of it will be 0. So this matrix A is also an important matrix. So since we are on K by K matrix, the nilpotent index is bounded by K. So A to the K is 0, but A to the K is this, and we get a contradiction. Okay? So the image of this polynomial is not a vector subspace. This is a well-known example and shows that we need the condition that the polynomial must be multilinear. Right? Okay, let's see some results, some positive results of this conjecture. It was proved by Kanarbelov, Malev, and Rowan that over quadratically closed fields, the conjecture is true for 2 by 2 matrices, and by Malev for the field of real numbers, that is also true. That is, the image is one of these 4 possibilities here. Also, Malev has some results for arbitrary fields, but we obtain this condition instead of only these 2 possibilities here. Still an important result. For 3 by 3 matrices, the same authors have this result, which shows that the possibilities are this. So here we have some possibilities which are not subspaces, but neither of these which are not subspaces have been shown to be the image of some polynomial. So for a 3 by 3 matrix, the problem is still open, even we have this interesting result here. Okay, here dense subset we mean with the Varisk topology. Okay, let's consider now some variations in this conjecture. We can consider now associative algebra A, or if you prefer a Lie, a Jordan, or some algebra in your favorite variety. Consider a polynomial. Here, if we're considering associative algebra, consider associative polynomial. Otherwise, you consider polynomial in your favorite free algebra, let's say. And ask if the image of F is a vector space. Okay, this question is interesting when we're dealing with simple algebras. Okay, for non-simple algebras, there are examples which are not subspaces. Okay, let's see some results with these non-associative settings. For example, here for the Lie algebra SL2, there are some results. For some other simple Lie algebras here for polynomials of low degree. For polynomials of degree 3, Jordan polynomials of degree 3, in the algebra of symmetric matrices. Also, some positive results for the rock, paper, scissors algebra. It's an interesting paper here. And this important result for the algebra of quaternions. Okay, so there is a lot of works. There are a lot of works in these directions of images of polynomials. You can find more of these on arXiv. Okay, let's see. For the problem we are interested in showing our results here, which is the algebra of K by K upper triangular matrices. We proved in 2018 that for polynomials of low degree, the image of F on the upper triangular matrices are the whole algebra. Here J, I'm representing the Jacobson radical of this algebra, which is the strictly upper triangular matrices, okay? Or J squared. That is, okay, J would be something like this. Okay, and J squared, we would have another line, another diagonal of zeros here. Okay, so each power you raise here, you have another 0 diagonal here. Okay, and in the same paper, we proved that the linear span, in the general case of some polynomial, some multilinear polynomial, must be the whole algebra or some power of the Jacobson radical here. Okay, so the conjecture is that this is true not only for the linear span, but for the image of a multilinear polynomial. Okay. Fagundes has also an interesting result in this direction when he worked with the algebra of strictly upper triangular matrices. Okay. Here we have some additional difficulties because the algebra has not units, so it's a little bit different, the approach. But he has a complete result here. Okay. He will present this in the conference tomorrow, this talk tomorrow. Well, what can we say about the complete solution for this problem for UTN? To handle this problem, we have defined this combinatorial tool we are calling the commutator degree. Okay, let's see what is the commutator degree of a polynomial. We have here the strictly descending chain of T ideals. Okay, here by this symbol, I mean the T ideal generated by S in the free associative algebra. Okay, the smallest T ideal which contains the set S. So we have this chain of T ideals. I'm using this because this is exactly the identities of the upper triangular matrices here of order 3. If you consider here, this is the ideal of identities of matrix of order R. Okay, and we say that a polynomial has commutator degree R if it lies in this T ideal and it doesn't lie in the next one. Okay, so knowing that who are the identities of upper triangular matrix is the same as saying that F lies in this T ideal and doesn't lie in this T ideal. So it's an identity for R by R upper triangular matrix, but not for matrices of size R plus 1. Okay, let's see from where does this idea of commutator degree comes from. If we have a unitary algebra here, and you consider a multilinear polynomial, you can easily prove these two facts. First, that if the sum of these coefficients, it's important to notice that any multilinear polynomial can be written this way, right? So if the sum of these coefficients is non-zero, then the image of this polynomial is the whole algebra. It's simple. So if you want to show that this is equal to some element A of your algebra, you just need to evaluate it on 1 and here on A over the sum of the coefficients. Okay, so every element is in the image, so we get this. And we also can prove that an element, polynomial F, lies in the T ideal generated by this commutator, if and only if the sum of its coefficients are 0. Okay, so here, this characterizes the multilinear polynomials with commutator degree 0, right? I mean, the elements which are here and which are not here. And this characterization is given only by looking at the coefficients of these polynomials, this polynomial, right? If their sum is different from 0, it lies here. If it's 0, it lies here. It's simple. So is it possible to do the same for commutator polynomials of higher commutator degree, not only for commutator degree 0? So this is what we're going to talk about now. Yes, it's possible, but you need to consider some subsets of permutations here. We are denoting this way. So first, we are partitionating our set 1 to m here in this way. Here, this m is the number of variables of our polynomial, right? Here. And we are partitionating it this way. I'm going to call this T, capital T, and this small t, right? So I'm defining this, and the number of elements here is equal to k. So I'm defining the set of permutations as kt, capital T, small t, in the following way. We are considering, so we have this partition, we are considering the first h1 minus 1 elements, and consider all permutations. We take these elements to this first set here. Okay, then we are the h1, the next element here in the sequence will be, its image must be t1. And we go on this way. So we have some blocks here. First block, and here we have h1, second block, h2, and so on. So the element from here, when we apply sigma, must be in T1. This, when I apply sigma, must be this element T1 here, this number T1 here. This, when we apply sigma, must go to another subset T2, and so on. Okay? We do this. And we consider all permutations which do this. Okay, here, the elements are in order. It starts with 1 and ends with m. Here, we are considering permutations, right? So the order is changed here. But all these elements must come to here in some order. This element must have exactly this image. These elements must come to here, and so on. Okay? Well, doing this, the set of all permutations satisfying this will be denoted by this symbol here, Sk, capital T, small t. Okay, this k is the number of parts we consider here. This number H1 here is one more of the number of elements of this set T1 and so on. Okay, right. Now we are considering the set sum of all coefficients which are indexed by these elements, and we are denoting it by this symbol beta here. Okay, so beta is the sum of all coefficients lying in that set. Okay, and with that we can characterize the polynomials of commutator degree R. Not any polynomial, but multilinear polynomials, of course. So a polynomial has commutator degree R if and only if all these guys are 0 for value is k less than R, and this is not 0 for some choice of t and t, for some partition I have considered when we are considering k equals R. For some partition R elements, right? So this theorem characterizes these polynomials of commutator degree R. Now we have a hope to use this theorem to solve the problem of characterizing the image of a multilinear polynomial of commutator degree R, as we know in this case, because commutator degree 0 means image is the whole algebra. And now we want to apply this to commutator degree R. So this is the result we have obtained. That F is a multilinear polynomial, then its image on upper triangular matrices is J to the R, if and only if it has commutator degree R. Okay, here, remembering this is the set, the nth power of the Jacobson radical, which is the set of upper triangular matrices with 0 in the first R diagonals, right? So this is a complete result for this algebra. And I can give you the idea of how we prove this. So we need to, given a matrix here, we need to find matrices C1 and Cm such that this evaluation gives A. So we're considering it has commutator degree R. Then there is some partition such that that coefficient I have just defined is non-zero. Using this fact, we can consider a specific substitution of these variables by some diagonal matrices if they are in those elements T, those parts T of the partition, and those which are defined by Ti's will be defined as some nilpotent matrices here. Actually, some matrices of this form. Okay. Actually, this for I less than n and CTN. Sorry, m here, and CTN for a more general matrix. And then, using this fact, we are able to find these specific substitutions which solve this problem. Okay, this result is on arXiv, if you want to see, and it's accepted for publication in Israel Journal of Mathematics. Just to say some similar problem here, we can consider this descending chain of T-ideals. I mean, the T-ideal generated by a standard polynomial, and we can ask, we can say that a polynomial has st degree k if it lies here and it doesn't lie here. It would be interesting to know if there is a characterization of these multilinear polynomials in this st degree k by means of its coefficients, right? Maybe not this, but you can maybe change this by st4, st6, the even ones. Maybe it may be interesting to understand a little bit more the problem of images of full matrix algebra. Okay, so that's it. Thank you.
Thank you. Have you questions, comments? Can see the
one remark, maybe Turkey. Can we generalize the results to a finite dimensional incidence algebras?
Can you, there is a question from the hall. Can you generalize your results to the case of finite dimensional incidence algebras?
No, for instance, for finite dimensional incidence algebras, there are counterexamples. The result is not true. There is you can find on arXiv a paper of Felipe Asumura and Inês Santulo, which they tried to solve this complete problem, but later they found an error. But in that paper, they show a counterexample on incidence algebras.
Okay.
So it's not true. It will be interesting to know in which incidence algebras this is true, but it may be a difficult problem.
Well, the whole thanks you for this answer. Other questions? Probably I would like to ask, there is similar problem about the image of a word in a finite group.
Yes.
Is it possible to apply results on this group theoretic problem to the ring theoretic case? Not, I don't mean this necessarily this particular case, but to the ring theoretic version of the problem, considering, for example, group rings over certain finite groups, in cases where there are non-trivial results on this group theoretic problem.
Yeah, I don't know. I believe not, because to work with groups is much more difficult than working with algebras. But I don't know. I can't say anything about this.
Okay. Thank you. Other questions?
Thank you. Well,
if there are no more questions, comments, or remarks, let's thank again Tiago Castillo de Mello. Talk. And
thank you.
Thank you. And let's continue with the next talk. The speaker is Vladimir Gerdzikov, and the title of the talk is Recursion Operators and Hierarchies of Nonlinear Evolution Equations related to Kac-Moody algebras. Please, Professor Gerdzikov. Thank you. Okay.
Thank you, Mr. Chairman. Well, I changed slightly the title of the talk, but the contents will be basically the same. So now it is Kac-Moody algebras and integrable equations. So, okay. The plan of the talk, I'll do some introduction and we'll explain what does Kac-Moody algebra and integrable equations mean. Then I will demonstrate that using the inverse scattering method, one can solve soliton equations which allow lax representations in terms of Kac-Moody algebras. We shall see how the recursion operators appear in these lax representations, and we shall see that they are responsible for the general properties of the soliton equations. It is a wide topic. If I have some time, I will say also about the hierarchies of Hamiltonian structures and other things. But in 20 minutes, one cannot do a lot. This is a short list of papers in which most of my results have been published. I will talk mainly about the first one, this one, which came out recently in theoretical and mathematical physics, in which we consider Kac-Moody algebras of the type D4. D4 twisted and the two twisted versions of D4. The other publications of mine concerned with the general structure of the method and more general results. Okay, so as I promised, I will tell you what are Kac-Moody algebras and what are integrable or soliton equations. Integrable or soliton equations are a special class of nonlinear partial differential equations that can be solved by the inverse scattering methods. In the next couple of slides, I will explain precisely what that means, and I will tell you, of course, also about the Kac-Moody algebras and how are they related to the lax representation or lax pairs. These integrable equations are characteristic by possessing lax pairs and lax representations, and this means that for each of these equations one can find two ordinary differential operators L and M, which are first order with respect to x, and sorry, it must be time here, not x, and which are matrix valued. I have matrix valued potentials, U and V. And these matrix valued potentials depend also on the spectral parameter lambda. So we shall request the lax representation, which means that these two operators, L and M, must commute identically with respect to the spectral parameter lambda. And we shall see how this allows us to solve the corresponding equation. I will start with a generic case where U of x and lambda is linear in the spectral parameter. X and T is the potential matrix. J is a diagonal matrix with some eigenvalues, J1 to Js. The other operator contains V as a potential, and it is polynomial in lambda up to a certain power.
And the highest power of lambda here again multiplies some diagonal matrix K, which has this eigenvalues K1 to Ks. So now we request that these two operators commute identically with respect to lambda. What is written here in this line is the commutation, the commutator of these two operators. So we have time derivative with Q, and that's why the equations will be evolution equations, always first derivative with respect to time. And then we have some polynomial in lambda, which contains the x derivative of v plus the commutator of these two potentials. We start to commute one after another, and we first find that J and K must commute. And of course they do, because they are diagonal matrices. When we take the next power in lambda, the nth power, we find that Q must be related to V1. In other words, V1 can be expressed in terms of Q like that. And then we put to zero all the other coefficients with positive powers of lambda. And what we obtain is something that you can tell as recursion relations for the coefficients of Vk. So Vk plus 1 commutator with J must be expressed through Vk like that. To solve this recursion relation, we have to split Vk into diagonal and off-diagonal parts. And after doing that, we find that the off-diagonal parts of Vk plus 1 can be expressed in terms of the Vk, off-diagonal part of Vk, with the help of the recursion operator lambda. And finally, it can be expressed as the action of this recursion operator onto V1. The off-diagonal part is also expressed through the diagonal part of Vk is expressed through the off-diagonal part of Vk like that. And the recursion operator lambda that appeared was given like this formal expression. It is integral differential operator, but we shall see that when it acts on Q, it produces local expressions, expressions which depend on Q and its x derivatives. Finally, the lambda-independent term of this commutation relation, it must also vanish. But now it vanishes only if Q satisfies this nonlinear evolution equation, which is called soliton equation, because it has a lot of applications in soliton physics. How to solve this equation? Well, this is known as the inverse scattering method. And suppose we have this equation and we have assumed that Q0 of x is the initial condition for our potential Q. And then what we can do is to consider the Lux operator for time equals 0. That is, we put Q0 of x as potential there. The next step is to solve the direct scattering problem for L0 and determine the scattering matrix of L. And step 3, which is a direct consequence of the last representation, means that the time derivative of the scattering matrix must satisfy this simple ordinary differential equation. And here must be K, not the J, I'm sorry. So the solution of this equation is given here. So in this way, we can define the scattering matrix of the Lux operator for any time, and it remains the last step to solve the soliton equation. That is, given the scattering matrix at any time t, we must determine the corresponding Lux operator that has this scattering matrix. And this is the inverse scattering problem for L. Why is this related to integrability? Well, first, each of the steps that I introduced above has unique solution. Second, from the evolution equation for the scattering matrix, we find that its diagonal elements have zero derivatives with respect to time. That is, they are time independent. And because they are functions of the spectral parameter, they produce an infinite number of integrals of motion. And okay, I now have to go faster because in this way I will not have enough time. The inverse scattering problem for these types of flux operators are basically reduced to Riemann-Hilbert problems, which come from the theory of analytical functions. Namely, for the simplest case, when the eigenvalues of J are real, we can introduce fundamental analytic solutions of the Lux operator, psi plus, which is analytic in the upper half plane at lambda, and psi minus, which is analytic in the lower half plane, and on the real axis, they are related linearly by this soaring function. And this soaring function has to have simple dependence on the spectral parameter, like this. And then Zakharov and Chabat proved that if we consider this solution of the Riemann-Hilbert problem, then we can construct the fundamental analytic solutions of the Lux operators, and eventually we can derive also some specific solutions of the soliton equation, namely its soliton solutions. The method of doing this is known as the Zakharov-Chabat-Dresent method. It was discovered many years ago. In a number of cases, one can determine also the action angle variables of this infinite dimensional, completely integrable Hamiltonian systems. Now, what are Kac-Moody algebras? Roughly speaking, Kac-Moody algebras are infinite dimensional algebras which can be constructed starting from a finite dimensional simple Lie algebra. And this is done like that. We take the coefficients Vi to belong to the algebra, and then we introduce this polynomial, or maybe Laurent polynomial, or Taylor polynomial, where n tends to take some integer values. The elements of the Kac-Moody algebras are formal series in lambda, and in addition, we can introduce gradient in this Kac-Moody algebra, and basically the gradient is done with the so-called Coxter automorphism. This automorphism has a finite order, and it may be just the Coxter automorphism, which is the element of the while group of the simple Lie algebra, or it may be this Coxter element composed with the external automorphism of the Lie algebra. So each time we have Coxter automorphism, which is a finite order, and the number h, to which c to power h provides the unit element, is known as the Coxter number. So we can determine how the Coxter automorphism acts on the system of roots of this simple Lie algebra. And in addition, we can use this Coxter element to introduce a gradient in the algebra, namely to split the algebra into H subspaces, GK, which are the eigensubspaces of the Coxeter automorphism. Namely, acting on any element of GK, we obtain that it gets multiplied with the eigenvalue of the Coxeter automorphism. Here, omega is a root for the h of 1. Each of these subspaces has a basis, and the basic element, the basis in these subspaces can be introduced by taking the average on the action of the Coxeter automorphism. So E alpha are the Weil generators and Hj are the Cartan generators. Okay, let us consider now how this can be done for the special case when we choose the simple Lie algebra to be E4 or SO8. The root system of SO8 is as given here. Delta plus is the set of positive roots of SO8. Here below, alpha 1 through alpha 4 give the simple roots of the algebra SO8. And here we shall use also a slightly deformed notion of orthogonality. Namely, we shall say that the matrix X belongs to SO8 if it satisfies this relation S0x plus X transposed by S0 equals 0, where S0 contains plus and minus ones on the second diagonal. This is just for convenience. With this choice, we will have the Cartan basis represented by diagonal matrices. And here is the Cartan-Weil basis of the corresponding algebra. So this is for the simple roots. Of course, it can be extended easily for all the other roots of the algebra SO8. Now, as I mentioned, we will use the Cartan involution, the Cartan automorphism, Coxeter automorphism of the Lie algebra, which is C1 and which is composed by the reflections with respect to the simple roots of the Lie algebra. We have also another possibility. We can combine this Coxeter automorphism with the second order external automorphism here. This is the mirror reflection. And finally, we can combine the Coxeter automorphism, as shown here, with the third order automorphism of the Dynkin diagram. And of course, we will get three different gradings of D4, and the Coxeter numbers in the first, second, and third case are given here, 6, 8, and 12. Here are the eigenvalues of the Coxeter automorphism, which actually determine the exponents of the corresponding of the algebra D4 and its twisted versions. And in the right column, we have the ranks of the corresponding Kac-Moody twisted algebras. So here is how it can be done. We can evaluate the action of the Coxeter automorphism on the simple roots of the algebra, and we see that with each simple roots we can relate an orbit, and each these orbits O1 to O4 contains 6 elements. Now here the Coxeter element is the element from the Weil group, so its order is 6. What next? Sorry, these are the commutation relations.
which are not very difficult. In the second case, when we have Coxeter automorphism combined with the mirror reflection, we have another representation of this Coxeter automorphism acting on the roots. And now it is easy to check that its 8th power equals to the unit matrix, and therefore the Coxeter number now is 8. The eigenvalues of the Coxeter automorphism are this, omega 2 is root of order 8 of 1, and so 1, 3, 5, and 7 are the exponents of d4, 2. And then here are the orbits. Again, now we have 3 orbits containing 8 roots each. And this is the basis. We can introduce also the basis in the Cartan-Weil basis related to this algebra, which is given here. Finally, for D43, we introduce this Coxeter automorphism. Now one can check that this is the action of this automorphism on the root space, and its 12th power now gives the unit matrix. So now the Coxeter number is 12, and the exponents are 1, 5, 7, 11. How much time do I have?
3 minutes.
3 minutes, okay. So I don't have much time, as you understand. This Coxeter automorphism splits the roots of D4 into 2 orbits by 12 roots each. And okay, this is the Cartan-Weil basis compatible with this gradient. Now, what about the equations? Now, we use again Lax representation. Again, the potential of the Lax operator is Q minus 1 times the diagonal element. The second operator is again polynomial in K. Only what is different now is that the potential Q and must belong to the G0. Potential 3K must belong to the K subspace each, and K and J must belong to the intersection of the corresponding subspaces with the Cartan subalgebra. So it is they will be non-vanishing only if the powers of lambda n and the power 1 are exponents of the algebra. 1 is always exponent, so okay. Here are the recursion relations which are satisfied by the coefficients Vk, and they are solved in a very similar way as in the generic case. So the only difference now is that we get several types of recursion operators. One of them is recursion operator that is related to that is acting on the subspace GS, where S is an exponent of the algebra. It is a different case when it acts on a subspace which number is not exponent. So it is quite abbreviated here. And finally, we have also a hierarchy of modified KdV equations related to each of these algebras. So this is the hierarchy related with D41. Now the potential Q is has 4 independent functions in it. And this is the generic form of all these possible equations. Here, since 3 is a double valued exponent, we have a little bit diversity here. For D42, we have a bit more complicated situation, which is given by these 4 sets of hierarchies. And finally, for D43, we have these expressions in terms of the recursion operators. So just 1 minute more, I'll show you how the Hamiltonians of these soliton equations look like. Here is for D41, we have 2 independent Hamiltonians here. Each of them has 3rd order derivative here. And you see they have cubic nonlinearities. For D42, we have this Hamiltonian. Again, here 3 is exponent, so it is also 3rd order with respect to x. And finally, for D43, this is the most difficult case. And here we had 2 functions, p and q, which determine the equations, and here are the expressions for p and q. Okay, so it's there are a lot of problems that are still left open, and this is how to construct the soliton solutions. That is how to apply the Drensky method, how to define tension angle variables, and a lot more.
Thank you.
Thank you.
Any questions or comments? If there are no, let's thank the speaker once again. Thank you. 4 minutes break.
Hello, everybody.
Okay. Our next talk will be given by Artyom Lopatin, and its title is Identities for a Parametric Via Algebra over Ring.
Yes, thank you for the introduction, and I'm very grateful for organizers for giving me the opportunity to give a talk. Okay, now I'll share the screen, and we'll see how it works. Okay. Does it work now? Okay, I can't see slides. Okay. So my screen is shared, yes. So can anyone see my slides or no?
Yes, it's shared.
Yeah, they're shared, perfect, but I can't see them. Okay. So then I can start. So here's the title. So here's the title, Identities for a Parametric Via Algebra. This work is done by me and together with Carlos Arturo Rodriguez Palma. I'm from Campinas and he's from Bucaramanga. And so he was my former PhD student, so it's our joint work. Okay, so at first I would like to start with some basic definitions. Okay, so we work over the field f of arbitrary characteristic. Normally we assume that the field f is infinite, but sometimes we assume that it is finite. And we have here notation for non-commutative polynomials and notation for commutative polynomials over some fixed F algebra B. So we have here some fixed F algebra B with unity, and we will work with it. So obviously we have a classical definition of Weil algebra, which is given here. So it's a factor of non-commutative polynomials by relation epsilon x minus x epsilon minus 1 equal to 0. In other words, we have here that x and y are commutative, but we should pay a price for commutativity with minus 1. And so while algebra is well studied, especially automorphism of it are well studied, a lot of things are known about it, and obviously it has some generalizations. So here we consider some generalizations. And probably first generalization of Weil algebra, okay, not the first, but one of the most well-known, was by Bavula in 1993, so-called generalized Weil algebra. And so Bavula studied it, published a lot of papers about this algebra, but in this talk I will not talk actually about this generalization. I will concentrate on another one, which 6 years ago was introduced by Benkat, Lopez, and Ondros in 2015. They published a paper in Transactions of American Mathematical Society about this algebra. And so their generalization is called a parametric family of subalgebras of Weil algebra. And the definition is the following one. So instead of this one, they put some arbitrary polynomial in X, so this coefficient in field F. So this polynomial, of course, is fixed, and because they consider H as a parameter, so it's called parametric family, because they, depending on H, they obtain a family of subalgebras. And here, AH is actually subalgebra of common Weil algebra. And so they studied these algebras. Of course, their prime questions of interest were what can be said about automorphism, what can be said about representational theory, some general
algebraic properties of this algebra. And actually, it should be noticed that these two notions, they are not the same, they are different. And in their paper, Benkart, Lopez, and Andrews, they showed that this notion cannot be obtained as a generalized Weil algebra by Bazula. Another thing about this new type of Weil algebras was that recently, I guess last year, Babula published one paper about this parametric Weil, parametric family of superalgebras of Weil algebra, and I guess in August this year, he also put two preprints in archive about this algebra, but he was concentrated on automorphism of this algebra. And so what we are going to consider in this talk, we considered factorized Weil algebra over arbitrary algebra. So now I'm going to give explicit definition. So here we fix some unital associative algebra B over field F, and we fix also some polynomial H, X is variable, and coefficient are from the center of B. And so what we obtain, we call a parametric Weil algebra. So it's defined as a quotient of non-associative polynomials in X and Y over B with relation epsilon X minus X epsilon is equal to H. So here, and definition is like in case of Benkart, Lopez, and Andrews. Only instead of field F, we consider arbitrary algebra B, which is unital, of course, associative, and we have here a restriction on H that coefficient of H are from the center of B. This restriction is crucial, without it, nothing works. Well, obviously, this, and we call it parametric Weil algebra. Obviously, this parametric Weil algebra is generalization of algebras considered by Benkart, Lopez, and Andrews. And we can also make some remark that if H has coefficients in field F, then this our algebra is just in the product of algebra considered by Benkart, Lopez, and Andrews and algebra B, so it's not very interesting object. And but of course, when coefficients of H are not in field F, we don't have this kind of isomorphism, because then this algebra is not defined or field F. And so here's some motivational lemma why it makes sense to consider these kind of parametric Weil algebras. But before this lemma, I would like to make a remark that, of course, these generalization are partial cases of Rohr extensions. Here I'm not given the definition of Rohr extension because it's well known. And yes, there are partial cases of it, and probably you can ask why not to represent extension, but it's very general construction and not always possible to say a lot of things about the algebra which we obtain as a result of this extension. So we have the following lemma, which was published by Awami, Van den Berg, and Wallenstein many years ago. And so here is the definition of our extension. So epsilon is a variable, R is a ring, which we have a ring. We consider extension is variable epsilon. Sigma is endomorphism in general case, but here we assume in this lemma that it's automorphism, and delta is sigma duration. So in this lemma, we don't have any restrictions on delta, on duration, on sigma duration delta. And in this lemma, R is a ring of polynomials with coefficient in F. And so when we have these conditions, then algebra A is isomorphic to one of the following algebra. First one is a quantum plane. Then we have a quantized Weil algebra, so definitions are given here. And the final algebra is exactly this parametric family of subalgebras of Weil algebra, which were introduced by Benkart, Lopez, and Andrews. So this is a motivational lemma for why it makes sense to consider these parametric families. Okay, and so in our work, we will impose the following restriction on H, on polynomial H. Restriction is the following one, that the leading coefficient of H is not zero division. at the end of my talk, I will show you that we really need this restriction. And so our problem with which we are going to work is the following one, is to describe the ideal of polynomial identities for this parametric Weil algebra. In other words, to describe ideal of polynomial identities. And so, but before formulating our result, I'm going to say a couple of words about a non-result. So of course we know that if characteristic is 0, then algebra of Weil doesn't have any identities at all. This is a very simple result. It can be proven by Kaplansky theorem, let's say in, I don't know, 3 lines maybe. But nevertheless, it makes sense to think about polynomial identities in case of 0 characteristic. But polynomial identity is not algebra of Weil, but polynomial identities of some subspaces of it. So here, let me consider nth Weil algebra. So it's obtained by, in a Weil algebra, we have 2 variables, x and y. And in nth Weil algebra, we have n pairs of variables. So the definition is given here. So here, xi and xj, they are commutative. Epsilon I and epsilon j are commutative as well. Xi and epsilon j are commutative if I is not equal to j. But if and xi and epsilon I, they are not commutative. They are commutative in the same sense that are in the case of Weil algebra. So we have to pay the price of putting 1 if we would like to commute them. And so some identities of some subspaces in case of 0 characteristic was studied by Jumadildaev in 2004-2014. And so let me show you these results. But before this, I need to define some subspaces. So the first subspace which I'm going to consider is this one. So if F span of products xi epsilon j. And the second subspace is the F span of products of A. A is any polynomial in variables x1, x2 until xn, and variables xj1, a epsilon j2 until epsilon jr. So we consider these 2 subspaces, and then there are following results. So the standard polynomial is a polynomial identity for this subspace in case we have this restriction in case n is greater or equal n squared plus 2n. Then standard polynomial is not a polynomial identity for this subspace if we have the following condition. Another property is that the standard polynomial is a polynomial identity in case we have just 1 pair of variables. And here condition is if and only if. And then in case we consider just pair of variables, we know by the results of Jumadildaev, of course, that the minimal degree of non-trivial polynomial identity is 2r plus 1. And finally, there is a result by Jumadildaev in 2015 that the standard polynomial of degree 2n is a polynomial identity for this subspace if and only if n is equal 1, 2, and 3. So some research was done in this direction. As about the field of positive characteristic, there are no any results about it. And before formulating our results, I would like to show you some connection with algebra. So if you consider this subspace with multiplication given by Lie bracket, it's exactly ends with algebra. Exactly ends with algebra, which is of course is a simple infinitely dimensional Lie algebra. And there is an interesting problem to study identities of with algebra. Of course, there are certain results about it, but I guess we are still far from completely understanding its identities. And in particular, in case of one variable and in case of characteristic 0, so here characteristic is 0, there is a following open conjecture that all polynomial identities of with algebra follow from the standard Lie identity, which is given here. So this conjecture is still open, and okay, but so it's quite interesting problem. And so between associative identities of these subspaces and Lie identities of bit algebra. Obviously, there exists some connection, and so it can be considered as a possible application of our results to try to apply them for bit algebra. And so now I'm going to formulate results. So here I assume that a restriction star holds. So restriction star holds. And if characteristic is 0, then we have the same situation as in classical case, namely we don't have any non-trivial polynomial identities, which was more or less clear. Assume now that characteristic is positive and field is infinite. And then we need some additional condition. Which says that there exists alpha from the center of algebra B, such that H alpha is not zero divisor. In this case, identities for parameterized Weil algebra are the same as identities of P by P matrices over algebra B. Here, obviously, by identity, I mean usual polynomial identity with coefficients in field F. So these two algebras are PI equivalent. And this result has some nice application to the case when B is actually equal to F. In other words, to the parameterized Weil algebras which were introduced by Benkert, Lopez, and Andrews. So here we don't have this additional condition, and we just can formulate that here identities of parameterized Weil algebra are the same as P by P identities of P by P matrices over the field F. So our main result, of course, is this one. It's part 3, just some simple corollary. And here, as you noticed, I mentioned this restriction star. And so actually this restriction is essential. But before showing that this restriction is essential, let me consider the case of finite field. Actually, I assume that field F is finite. And so we may try to ask, maybe the same result holds for finite fields. And the answer is no, it doesn't hold, and it can easily be shown that identities of parameterized Weil algebra over the field F are not the same as P by P matrices over the field F. It can easily be shown because we know one identity of P by P matrices over a finite field F by result of Genov. And so we can show that this identity does not hold in parameterized Weil algebra. So these two algebras do not have the same identities. And we have here the following conjecture, which is we consider some infinite field K, which contains our finite field F, and then ideal of identities of parameterized Weil algebra are the same as identities of P by P matrices or infinite field K. So these identities are, of course, with coefficients in field K, and we take intersection with non-commutative polynomials with coefficients in the F. So essentially speaking, this conjecture says that in case of finite field, we'll get the same result in the case of infinite field. And we have similar conjecture in case of arbitrary unital algebra B. And here this counterexample, which shows that we actually need this restriction star. So we can consider as algebra B the algebra of double numbers. So it's two-dimensional algebra generated by 1 and epsilon, where epsilon squared is equal to 0 and 1 is a 1. And as polynomial H, we take epsilon. Then in case F is infinite field, we have the following description of identities of this parameterized Weil algebra. So ideal of identities is generated by these two identities. It can be shown. So here we need that field F is infinite. And in particular, we have that this algebra is not PI equivalent to the algebra of T by T matrices for any T greater or equal to 2 and any C algebra with unity. And we, as a consequence, we have the following result. Let us denote by GK. It's Grassmann algebra with unity of rank K. And then these are parameterized file algebra have the same identities as this Grassmann algebra of rank K, if and only if K is equal to 2 or 3. So we'll get this result. And then I can say a couple of words about further possible generalizations of this construction. Of course, here we considered this algebra B, and so instead of considering one pair of variables, we can consider several pairs of variables. And we can define multiparametric file algebra as given here. So instead of considering one polynomial h, we consider h1, hn. They're all polynomials with coefficient in center of B. And ideal I here is generated by the commutativity of variables xi, xj, epsilon I, epsilon j, xi and epsilon j when I is not equal to j and this relation. And so we can define multiparametric file algebra by this manner and ask exactly the same question, what are identities, and actually more or less clear that our method should work here as well. So here, that is it. Thank you for your attention. Okay, so my talk is finished.
Do you hear me?
Yes, yes, I hear you.
Вы меня слышите?
Yeah, да, я слышу вас.
Do you hear me?
Yes, yes.
Sound was dropped. We didn't hear you for a couple of minutes.
You were unable to hear me for a couple of minutes.
Yes, yes.
Oh, it's terrible. I wasn't able to see, I mean, can you hear me or not? Because, okay, anyway, my talk is finished, so I don't know.
Okay.
What else can be said?
You have finished your talk?
Yes, yes.
Okay, thank you. Do you have questions? Matthias Domokos has a question. Seems to me.
Yes. So why is this algebra AH a subalgebra of the Weil algebra?
Why H is subalgebra file algebra? Okay, I can try to share the screen to once again, probably I will not turn off the sound again. So the screen is shared, I guess. Can you hear me? Can you please confirm that you can hear me? Yes.
Yes, I hear you.
Yeah, okay, perfect. And so it can quite easily be shown. So your question is why this H agar is a subalgebra of H1, yes?
Yes.
Yes.
Well, it can be explicitly shown, embedding can be constructed. So we can send X to X here, and epsilon we can send to H epsilon. And epsilon we can send it, yeah, well, this embedding can be explicitly constructed. Let's put it this way.
Yeah, thank you.
So it's quite easy to do.
Other questions?
Yes, I probably wanted, first of all, to mention that first study of this type of generalization of while algebra was considered for polynomial when the effort of x is just x squared, this famous
Yes, okay, yes, Beckett, as I mentioned, this is,
there was established, there was a connection between Bavula generalization of while algebra, or there was also actually equivalent but formulated differently Rosenberg generalization of while algebra. And this simple example, Jordan plane, is inside these two classes. It could be shown. But you said that in general, these are not related. Was it somehow proved, or was it?
Yes, they in their paper they published the following result, which says that if we work over, okay, so when we consider generalized while algebra by Bavula, we should start with some ring, yes, with some algebra, and if we start from polynomials with one variable, then we can find some algebra such that it cannot be represented as generalized while algebra by Bavula. So as I get in construction of Bavula, at first, as let's say, as in the definition of or extension, they start with some algebra, yes. And so if we consider generalized while algebra for this ring, yes, for the ring of polynomials in one variable over field f, then it's not equivalent. Then we cannot get AH. Then we cannot get this parametric algebra.
So there is no kind of change of variables which will make it in this shape, or because
probably if they start with something else here in construction of Bavula, then I don't know, maybe. But you see, Bavula himself, he published like 3 papers about this algebra. And so if it's like the same, I guess he would mention it somehow. Of course, Bavula called this algebra not parametric family, it called it simply or extension of some kind.
Yeah,
but he himself published 3 papers about
somehow,
one paper is published, 2 submitted.
Yeah, maybe he even, yeah, but maybe some hidden connection still exists, because it's very non-obvious connection with, in case of Jordan plane, this connection to this class. It's, you should do some subtle change of variables to see this. Not immediate.
And so in case of this Jordan plane, it's also generalized while algebra, yes?
Yeah.
Okay, interesting. Yeah, okay, maybe. I don't know.
Yeah.
Okay. I think I'm afraid there is no more time for further questions. So let's thank the speaker once again. Let's take a 5-minute break.
Okay, Mr. Chairman,
Can you see the screen?
Yes, and the screen too. Here and here.
Okay.
Superalgebras.
Yes, so I start in 4 minutes.
Yes, yes.
Алло, вы меня слышите?
Да.
Слышите?
Yes, yes.
Хотел бы спросить, вы говорите по-русски?
Да.
Замечательно. Ваша конструкция связана каким-то образом с построением скобок Пуассона, исходя из копий соединенных орбит простых алгебр?
Простите, построение скобок Пуассона, исходя из чего?
Берете простую алгебру, берете коприсоединенную орбиту, и на этой алгебре естественным образом есть скобки Пуассона.
Да, вот я об этом буду говорить тоже. Да.
Хорошо, спасибо.
Well, perhaps we can start.
Yes.
It's time for the last talk for today. So I would like to welcome the speaker, Professor Zelmanov, and to note that the title of the talk is Poisson brackets and related superalgebras.
Thank you. Should I start?
Yes.
Okay. You know, this is the conference in honor of Vesselin Drensky, and we should discuss the areas that are close to his research. But fortunately, the research interests of Vesselin are so wide that one can speak almost about any subject. So I will talk about brackets and superalgebras. Let us start from the beginning. Let A be an associative commutative algebra. A bracket is just a binary bilinear product. It's just another word for a product. A bracket is called a Poisson bracket if it defines the structure of a Lie algebra on the associative commutative algebra A, and second, if you fix one of the variables, then with respect to the other one, it's a derivation. So you have a product rule. If you open any book on classical mechanics with high probability in the first chapter, you will see the Poisson bracket due to Hamilton. Here it is, where the algebra A is a polynomial algebra on 2n variables. Another example. Let L be an arbitrary Lie algebra. Let us consider the polynomial algebra on the vector space L. Well, it means you choose some basis in the vector space L, and elements of this basis are variables of your polynomial algebra, are generators of your polynomial algebra. If you choose another basis, it's like a change of variables. So we consider the polynomial algebra on the vector space L. And then the Lie product on, then L is a subspace of this algebra. And the Lie product on L can be uniquely extended to a Poisson bracket on the algebra A. In general, because of the product rule, every Poisson bracket is uniquely defined by values on generators. But not values on generators can be extended to a Poisson bracket. But in this case, the Lie bracket on L can be extended to a Poisson bracket on the polynomial algebra. There are brackets that are very interesting, but they are not Poisson brackets. For example, vector fields on a line. If you consider the algebra of polynomials, say in one variable, and this bracket, it's not Poisson. In order to incorporate this example, we will introduce a definition which is wider than Poisson brackets, the so-called contact brackets. You know, in a Poisson bracket, if one of the variables is identity, then the value is equal to 0. Any derivation is equal to 0 on the identity element. But in contact brackets, this is not necessarily the case. But if you fix one variable, the identity element, then with respect to the other variable, it's a derivation, maybe non-zero derivation. The second axiom is that the structure that we get on the algebra A is a Lie algebra, like in Poisson brackets. And the third one is a variant of a product rule, but not precisely the product rule. Here it is. So a bracket that satisfies all three conditions is called a contact bracket. For example, this bracket on polynomials in one variable is a contact bracket. Every Poisson bracket is a contact bracket if you choose 0 derivation. Another example. Let us, we define Poisson brackets on polynomials in even number of variables. Now let's consider polynomials in an odd number of variables. Here they are. The derivation is a usual partial derivative with respect to t or this. Of course, you can consider many derivations, but all of them basically boil down to this two. And then we will define values of the bracket on all generators. In this way, that is the same as in Poisson bracket. And these formulas. Of course, not all values on generators extend to a contact bracket, but these ones extend. And we get a contact bracket on this algebra. Our goal is to study Lie algebras that arise from Poisson and contact brackets. Some interesting examples are Lie algebras of Cartan type. Hamiltonian Lie algebra, it arises from the Poisson brackets that I described. And this is a contact Lie algebra, it arises from the contact bracket that I described. And there will be more examples later. In 60s, Herstein decided to study connections between an associative algebra A and the adjoint Lie algebra, where you replace the associative product on R by commutator. More precisely, he formulated a program which consisted of many problems, and the program was to study the connection between the associative algebra R and the square of the adjoint Lie algebra. Why the square? We will see later, and there are more connections between this square and R. So Herstein formulated a number of conjectures, and all of them have been proved at the turn of the millennium by Baydar, Breshar, Chebotar, and Martindale. Why did I mention this program? Because our program to study the connection between Poisson algebra or contact algebra and the corresponding Lie algebra is very parallel to Herstein's program. Why? You know, we could define a Poisson bracket on a non-commutative algebra in absolutely the same way. The example is commutator. Then the commutator is a Poisson bracket. It defines the structure of a Lie algebra, and if you fix one variable, then with respect to the other one, it is a derivation. But there is a result by Farkas and Letzter that if A is a non-commutative prime algebra, then basically all Poisson brackets are multiples of this commutator. So the only Poisson bracket is a commutator. So that underscores the analogies. Recently, there have been other approaches to study non-commutative Poisson bracket, like double brackets of Van der Berg, but we won't talk about it now. Though you again can ask many questions about the connection about the double Lie algebra that arises in this way and the double Poisson bracket. Let us consider the Poisson center of the Poisson algebra, but I hope that Farkas-Letzter theorem explains why we always assume that our algebra A is associative and commutative. Because in non-commutative case, there are none. So let's consider the Poisson center. Recently, Al-Ahmadi and Al-Sulami made the first step in this program. They showed that if A is a simple Poisson algebra, so it does not contain proper ideals that are invariant with respect to the Poisson bracket, then the square of the Lie algebra in question, modulo the center, is a simple Lie algebra. For those who are familiar with Herstein's theorem, it's a direct analog of it. So in this way, we get many simple algebras. Some questions. Let A, which are also similar to Herstein's questions. Let A be a simple Poisson algebra. To which extent this Lie algebra determines A? More precisely, if you have two simple Poisson algebras and there is an isomorphism between these algebras, does it imply that the Poisson algebras are isomorphic? And another question. Let A be a finitely generated associative commutative algebra with a Poisson bracket, Poisson or contact bracket. When is the corresponding Lie algebra finitely generated? When is it finitely presented? Generally very difficult questions, as we will see later. Now, for a Lie algebra L, let us consider the lower power series, that is the descending chain of powers, and the derived series, the descending chain of derived powers. Let G be a finite dimensional Lie algebra, and the characteristic of the ground field is 0. We consider the algebra of polynomials that I described above with the Poisson bracket. And we also consider the universal associative enveloping algebra. These two algebras are connected because the universal enveloping algebra has a filtration, ascending filtration of subalgebras, ascending filtration of subspaces. And the graded algebra associated to this filtration is precisely the algebra of polynomials. And the Poisson bracket then comes as a leading part of the commutator. In the recent joint paper with Al-Ahmadi, Al-Sulami, and Jain, we found the conditions for the corresponding Lie algebras to be finitely generated. This is not always the case. If you just consider, so we consider two Lie algebras, the Lie algebra of Poisson bracket and the adjoint Lie algebra of the universal enveloping algebra. If you just consider this Lie algebra, they are never finitely generated for a non-zero algebra G. If you consider powers or derived powers, then powers starting with the third one and derived powers starting with the second one are finitely generated if and only if the derived chain stabilizes at the second step. And that leaves open the case of this algebra, well, the second power or the first derived power. Then the stabilization in the second step is a necessary condition, but not sufficient. We have examples saying that, which show that even for these Lie algebras, there may be not finite generation for these algebras. So it's all very non-trivial. Now let us talk about superalgebras. Superalgebra is just an algebra graded by the cyclic group of order 2. So it is a direct sum of an even subspace and odd subspace. Whenever you multiply two even elements, you get an even element times odd element is odd, a product of two odd elements is even. Example, let's consider the Grassmann algebra. The Grassmann algebra is presented by generators and relations. These are generators and these are relations. So Grassmann variables anti-commute. Then the basis of the Grassmann algebra consists of ordered products. And we say that this product is even if the length is even. The product is odd if the length is odd. So the Grassmann algebra becomes a superalgebra. And if you consider, of course, the Grassmann algebras are embedded one into another. If you take the union, you get the Grassmann algebra on uncountably many variables. For any superalgebra, we can define its Grassmann envelope. It's a subalgebra of the tensor product. Now, let V be a variety of algebras. That is a class of algebras defined by some identities. Well, at this conference, everybody knows what is a variety of algebras, and everybody has his favorite variety of algebras or several. So let V be your favorite variety of algebras. We say that A is a V superalgebra if the Grassmann envelope lies on the variety, so it satisfies all identities. You can, you can take a generic arbitrary element of this tensor product, plug in it in the identities, expand brackets again, and get a bunch of graded identities. You can define super varieties in this way. But in this way, we get definition of an associative superalgebra, commutative superalgebra, Lie superalgebra, Jordan superalgebra, and so on. The Grassmann algebra is an associative commutative superalgebra, though it is not commutative as an algebra. Please feel free to interrupt me at any point and ask questions. Whenever I say something outrageous, just interrupt me. Okay, we can define analogs of Poisson and contact brackets on superalgebras. So this concept can be superized. For example, let A be an associative commutative superalgebra. A Poisson bracket is an operation bracket such that it defines a structure of a Lie superalgebra on A, and instead of product rule, we demand this. The rule is very simple. Whenever two elements interchange, like, here B goes before C, but here C goes before B. So you multiply by -1 to the power of the product of parities. Whenever you interchange two elements, don't forget to multiply by this -1. In the same way, you can define contact bracket. In early 70s, when these concepts were introduced, people even included these definitions in papers. Later, it became so standard that it's no longer included. It is understood. Examples of super brackets. Well, on a Grassmann algebra, superalgebra, we can define this. It's a Poisson bracket. You can define partial derivative with respect to an odd variable, and this is a Poisson bracket. And in some sense, it is similar to our first example, which arises in classical mechanics. Another example, which is also similar to one of our previous examples. Let us consider this associative commutative superalgebra. You can say that this is a tensor product, or you can say that this is a polynomial superalgebra in one even Laurent variable and n odd variables. In order to define a contact bracket, you have to start with a derivation. Again, we can consider partial derivative with respect to t or this. Since these concepts came from physics, they even have strange names. Ramon sector or Navier-Schwarz sector. And these are definitions of our bracket on generators, and it extends to a Poisson bracket on this algebra. And that gives rise to a Lie superalgebra. In physics, they are known as SON superconformal algebras, and they were introduced in the paper of Schoutens and in the paper of 12 Italian physicists. This is the alphabetically first one. These superalgebras are simple for all n except 4, and for 4, they are not simple, but the square is simple. That again explains why we focus on square, not on algebra itself. And here's the history. I have to explain what are superconformal algebras. There is a famous celebrated Virasoro algebra, the algebra of derivations of Laurent polynomials. It was introduced in the papers of Gelfand and Dorfman, or Gelfand, Bernstein. And it has a very interesting, well, the name Virasoro algebra is a counterexample to Arnold's principle. Arnold's principle says that every concept is named after the second person who introduced it. Virasoro is a counterexample. Virasoro was not the second person. Probably the first person was Richard Bloch, then Gelfand, then maybe Virasoro. Okay, it has a very interesting central extension, and it plays a very important role in many physical models. So physicists decided that since it is so important, why don't we find some superalgebra that contains Virasoro in the even part, and that has very similar properties, and maybe we will be able to introduce it in those models and get something interesting. And such superalgebras were found independently by Nevier-Schwarz and Ramon. They are known as Nevier-Schwarz and Ramon superalgebras, and then more superalgebras of this type were found by many, many people. And then Katz and van der Leur in '88 decided to bring some order to this area, and they defined the concept of a superconformal algebra abstractly. A superconformal algebra is a Lie superalgebra which is graded by integers, and the following conditions are satisfied. It is graded simple, so it does not contain any proper graded ideals. Second, dimensions of all homogeneous components are uniformly bounded from above. And third, it contains Virasoro in the even part, of course. Examples. If you consider this algebra of, well, super polynomials in one even Laurent variable t and n Grassmann variables, and take all super derivations, you get a superconformal algebra. It has interesting subalgebra, so special subalgebra defined by divergence, and then superalgebras K that I have already defined. And then in '96, independently, Chen, Katz, and Grossman, latest, Shepachkina constructed an exceptional, interesting superconformal algebra, which became known as CK6. Okay, and there is a conjecture that there are no other superconformal algebras, that's it. This is the list of all known superconformal algebras. And there are very good reasons to believe in this conjecture, but the conjecture is still open. In '88, three physicists, Fairley, Nutz, and Zakos, proved, if I read the names correctly, proved that Navier-Schwarz superalgebras and Ramon superalgebras are finitely presented. Finitely presented means that if you choose a finite, it is finitely generated, and in any finite system of generators, it is presented by finitely many relations. So they explicitly wrote these relations. Now, all the results below are joined with Consuelo Martinez and Zhou Zhang. Something strange happened with my, okay. So all the results are joined with Consuelo Martinez and Zhou Zhang. The first theorem, all known superconformal algebras are finitely presented. So we found finite presentations for all superconformal algebras. But we want to go further, and we want to introduce superconformal algebras on an arbitrary supervariety, not necessarily on a line. In other words, instead of Laurent polynomials in one variable, we will consider arbitrary finitely generated commutative algebras. So instead of lambda, we consider this tensor product. First, we have to define the corresponding superalgebras. And instead of W, we consider the Lie superalgebra of all derivations. Now, what is K? I won't say what is the analog of special Lie superalgebra. It's not quite clear what is the analog of divergence in this case. You know, these results are very fresh. So this question is not quite clear for us. But what is the analog of K? We will need to define a product of contact brackets, tensor product, but a special tensor product. So let A be a contact superalgebra. So an associative commutative superalgebra with a contact bracket. And let B be a graded associative commutative superalgebra with a Poisson bracket and with this property. Well, modeled after Grassmann algebra or after the Poisson algebra of classical mechanics. Then we can define a contact bracket on the tensor product that extends the brackets on A and B, so they are embeddable into this tensor product as bracket algebras. And the bracket on A and B is defined by this formula. The non-trivial part is that it extends to a contact bracket. Okay, but that allows us to define a contact bracket on this algebra, because we have a Poisson bracket on Gn. And that is really the generalization of algebras K1n, of SON superconformal algebras. This construction has a side effect. If A and B are simple and central, then it is not difficult to show that this tensor product is again a simple and central contact algebra. For example, if A is the algebra of truncated polynomials over field of prime characteristic and B is the Grassmann algebra, then we get a family of simple contact brackets on this algebra. And by the theorem of Al-Ahmadi al-Sulami, it gives rise to a family of simple finite-dimensional modular Lie superalgebras. At some point, well, some people already study simple modular finite-dimensional Lie superalgebras, and that gives a series of new examples. Okay, what about exceptional superconformal algebras? In '98, in a joint paper with Consuelo Martinez, we already defined these objects of an arbitrary associative commutative superalgebra with an inner derivation. So we will discuss the question whether these superalgebras are finitely presented. But this is a wrong question. Now, it's a wrong question to ask if these superalgebras are finitely presented. Now I will explain what is the right question. Let L be a perfect Lie superalgebra. Perfect means that it coincides with this square. A central cover is an epimorphism from some other perfect Lie algebra or superalgebra, such that the kernel lies in the center. So it is a central cover. Isaiah Schuh proved many years ago that there exists a universal central cover. Universal in the sense that for any other central cover, there is this homomorphism chi that makes the diagram commutative. Of course, Schuh did it for groups, but there is no difference. So it is a right question to ask about whether the universal central cover is finitely presented. And then everything depends on this kernel, or the universal kernel on the center. If it is finite dimensional, then the algebra L is also finitely presented. If it is infinite dimensional, then it is never finitely presented. Theorem, again, joined with Martinez and Zhang. Let A be a finitely generated associative commutative superalgebra, and let N be at least greater or equal than 3. So you need at least 3 odd variables. Then all the involved Lie superalgebras, that is their universal central covers, are finitely presented. Well, for the exceptional algebra, I did not mention the central cover. You see, there is no check here, because in 2003, we proved that these superalgebras are centrally closed. The universal central cover is itself. Now, what about these algebras? Why, when they are finitely presented? But it depends on the centers of these superalgebras, and these centers are very close to cyclic homologies of Alain Kohn of this algebra A. It depends only on the algebra A, doesn't depend on N. I am not ready yet to formulate the precise theorem, because this theorem is on the process. But in the classical case, when you have one even variable, one even Laurent variable, you know, cyclic homologies of the algebra of one Laurent variable is one-dimensional, so it's always finitely presented. In two variable, when you have two variables, it's infinite dimensional. And when you have one variable, but the characteristic of the ground field is prime, it's also infinite dimensional. Now, may I ask a difficult question? Is having odd variables good or bad? The standard approach was that the superalgebras are more complicated. In fact, in our problems, it's a blessing. You remember, I formulate the question, when the Lie algebra of brackets is finitely presented. It's a difficult question. Even the question, when it is finitely generated, is highly non-trivial. You remember the theorem about one particular bracket. But if you add at least 3 odd variables, then for this algebra, this is doable. Now, a few words about Jordan superalgebras. You see, I don't need to define Jordan superalgebras. I defined it for an arbitrary variety. Let A be a Poisson superalgebra. So an associative commutative algebra with a Poisson bracket. Let us double it. Let us consider the direct sum of 2 copies of the vector space A. And we define a multiplication. The multiplication on A, it's inherited from the product in A. When you want to multiply, you know, here is the multiplication. The non-trivial part is that when you multiply 2 elements from this subspace, you do it via the bracket. Isai Cantor proved that this superalgebra is always a Jordan superalgebra. It's called Cantor double. But there are brackets that are not Poisson brackets, and nevertheless, the Cantor double is a Jordan superalgebra. For example, if again you consider this bracket of vector fields on a line, The Cantor double is a Jordan superalgebra. Such brackets are called Jordan brackets. So a Jordan bracket is a bracket whose Cantor double is a Jordan superalgebra. Cantarini and Katz showed the Jordan brackets and contact brackets. It's virtually the same thing. You have a little bit modify one of them to get the other one. There is a one-to-one correspondence. This is virtually the same class. Now, I'm not going to define it because, well, people who know what is a Jordan algebra also know that by every Jordan algebra, you can construct a Lie algebra, which is called Tietz-Cantor-Köcher Lie algebra. And for every Jordan superalgebra, you can construct a Lie superalgebra, which is called Tietz-Cantor-Köcher. So Tietz-Cantor-Köcher construction. And we make an observation that the Tietz-Cantor-Köcher construction of a Cantor double is the defined, these Lie superalgebras that we defined above, in particular their central cover. Another theorem: for any finitely generated associative commutative superalgebra with any Jordan bracket, the Cantor double is finitely presented. Thank you. I finished.
Have you any questions, comments, remarks?
Yeah, maybe the question, which is kind of for this list of superconformal Lie algebras, what was the evidence that there are no others? How it is explained? What explanations exist?
Well, the first evidence was historical, and that in 88 there were no others. So the first conjecture was that there were no others, but then in 96, a new one was constructed, CK6. Now, what is the evidence that there are no others? If you impose a strong condition that all structure, without going into details, that all structural constants are polynomial functions, well, that can be reformulated in terms of so-called conformal or vertex algebras. Well, some strong additional condition, but very interesting one. Then Katz and Fattori proved that there are no others. And then if you look only at Lie superalgebras that come from Jordan superalgebras, as Tietz-Cantor-Köcher, in a joint paper with Victor Katz and Consuelo Martinez, we proved that there are no others. So in these two cases, there are no others. And the fourth reason, I believe it.
Yeah, most important one, of course. Yeah. So yeah, the second one is closer to kind of structural reason. So what I meant, others, any structural reasons why it should be the case, like.
But it's a highly non-trivial problem. Even in the case, forget about Lie superalgebras. This is the analog of the theorem of Olivier Mathieu, on Lie algebras with similar properties. And in 91, he published, I think it was 91 or late 80s, he published classification. And this classification is highly non-trivial. If you prove, it's highly non-trivial. So for superalgebras, it will be only more difficult.
Yeah. Yes, this is what I meant. Okay, Thank you for very nice talk.
Other questions and remarks? Surprising end of the talk, by the way. Do you hear me? No, yes. Do you hear me?
Yes.
Okay. As far as I understand, you have a question or remark, comment? Do you? Well, if there are no other questions, remarks, or comments, let's thank the speaker once again for the really
Чисто.
And this was well, this is the end of our this is the last talk for today. Tomorrow we continue at 10 a.m. Bulgarian time, which is 7 a.m. Greenwich Mean Time. So thank you again, and the session is over.
So, Efim, are you back to San Diego?
Excuse me?
Are you?
Yes, I'm in San Diego, yes.
San Diego.
And where are you?
In Israel. Back to Israel.
Well, it's great to see you.
Great to see you.
I have to go
Very
to
nice.
another meeting in Germany.
When?
See, now I'll have a meeting in Heidelberg.
Oh, no. Wow. Wow.
Bye.
So see you tomorrow.
Okay, bye.
Bye.
Ние нищо, тръгвам си полека, ще има...
Привет, План, не виждаш.
Здрасти. Тежко днес.
Може би трябваше да се взема и трето кафенце в някой момент.
Най-важното, че свърши вече. Днес поне. За утре се надявам да е по-спокойничко.
Аз също. Трябва да видим каква е програмата. Да, този хибриден вариант ми напомня, чел съм за тези, когато са се появили реактивните самолети, че старите летци по-трудно са усвоявали от съвсем начинаещите. Защото съвсем начинаещите са отраз почват да следят по прибори. Как е самолета, примерно при кацане, дали има наклон, дали е хоризонтален, като стария летец някак си вярва на интуицията. И понякога са се случвали происшествия.
Нищо трябва да е само да видим кой започва утре.
Ами сега ще ти кажа.
Не кой започва, кой е водещи утре. Христо Илиев. Той сигурно знае за това. Би трябвало да знае.
Ами Христо знае. Христо знае.
Ами значи няма проблем тогава. Защото виж, аз няма да се появя в 10 сутринта. Това означава да стана в 4 часа мое време тук, за да чуят докладите. Което бих могъл да го направя. С малко волеви усилия ще го направя, ама заслужава ли си?
Да. Между другото в Москва съм го правил това в може би 2 случая.
Recording stopped.
Трябваше в 6 часа на българската вяра. Значи да съм 4